presentation today as well. And so now I leave the microphone to Katia. She will be the chair of the next session from the University of Bologna. Thanks for joining us and helping in arranging everything. So you can start.
Okay, so just a few words. First of all, I would like to thank the organizer, Francesco, and Maria Assunta and Sonia, for the kind invitation to chair this session of this event in honor of Roberto Marassi. And I knew him when I was a student in the lab of Professor Mastragostino, and over time, I also worked in collaboration with his group in project that yesterday Professor Mastragostino mentioned. And also later, I had the opportunity to examine as external reviewer many of these excellent PhD students. And the presentation of the former student of Roberto yesterday and also today evidence the strong impact of Roberto mentoring and friendship on their successful career. And just to stay on this topic, the first contribution of this morning will be presented by Sonia Zocche and deals with polyox anions inspired by Roberto Marassi. Please, Sonia.
Thank you very much, Katia. I start sharing now. Can you see my screen, my presentation? Can you see my presentation? Yes.
Yes, Sonia, we see.
Okay, thank you. Thank you very much. And I'm really happy that we managed to bring together most part of the alumni of Roberto and many of the collaborator of Roberto in this symposium. And I would like especially to thank Francesco, that is the key person here, and invited me and Maria Assunta to be part of the organization. And the title I was thinking today, I would like to speak about a topic that I started to work with when I was a postdoc in the group of Roberto. And then I still bring forward a topic on the polyoxometallate in a different type of energy storage system. I want to start this picture. So I know Roberto since my PhD started in 2002 and until 2005, when I was working with lithium-ion batteries, in particular with graphite anode materials for lithium-ion batteries. And this was picture taken during my PhD with the group of that time. And after that, I remained some few years in the group as a postdoc. And the first time that we had the idea to use the polyoxometallate was as a catalyst, or better, co-catalyst for fuel cell. And this was a project that yesterday Professor Marina Mastragostino was also describing in relation to development of fuel cell, which was bringing together many different groups. And this work was collaborative work with different groups, including Professor Scosati and Professor Pavel Kulesha from Warsaw University. And in this context, we've developed a new catalyst based on insoluble salts, so cesium salt of polyoxometallates of phosphotungsten salt. And we tested the behavior toward the oxygen reduction reaction in the fuel cells. And so among different applications, so if you look in literature, you find an application of polyoxometallate in the fuel cell as a catalyst, but also in the membranes. But also it's possible to find application of polyoxometallate in the liquid form in a redox flow cell. And as well, sorry, there is some microphone on. I don't know if somebody can switch off microphone. There is some noise in background. Sorry, there are some microphone on from somebody in the background. Okay, we are also using polyoxometallate in metal-ion batteries. For instance, in my group, we are working for lithium-ion battery. it's exactly the same type of material, so cesium, salt of polyoxometallate used in a lithium-ion battery. And recently, I also start using this material in a hybrid device, so a supercapacitor with a redox electrolyte, where the polyoxometallate is in its liquid form in a similar way like in a redox flow cell, but in this case, the system is a closed system. I will go for the rest of the presentation to speak a little bit more in detail about this topic. So just a short background about a supercapacitor with a redox active electrolyte. Normally, you have two identical electrodes, which are based on a very high surface area carbon, and the energy is stored via double layer. And if you have a redox species dissolved in electrolyte, you can add additional energy storage via Faraday reaction. So the redox species will oxidize, will reduce at one electrode, and another redox species can oxidize at the other electrode. So it's an hybrid system when we have a double layer capacitance and the Faraday reaction coming from the redox species, which is in the electrolyte. As an hybrid system, this will show electrochemical signature, which are in between a battery and a double layer capacitor. So in a battery, normally you can observe in a cyclic voltammetry well-defined redox peaks, and you will observe a plateau in the galvanostatic charge and discharge profile, while in a DLC, you observe only double layer current. So you will not observe Faraday peaks, and this is also translated in a sloped curve in the galvanostatic charge and discharge. And in the case of a hybrid system, you have a mixture of the two components. So we have a double layer with superimposed redox peaks, and the galvanostatic profile will be in between the two systems, battery and the double layer capacitor. And in the context of redox electrolytes, there are different types of species that can be used. And one of the collaborators of Roberto, so Pavel Kulesha, together with Magdalena Skunino-Koska, already started to investigate this system by inserting the phosphotungstic acid as a redox electrolyte. And in aqueous solution, you will observe very well-defined multi-step reactions. So the polyoxometallate undergo multi-step reduction here, with the reduction is occurring at the tungstenum redox center. And Magdalena was proposing this system where you have two electrodes which are carbon-based materials. And in one compartment, we have the reduction of the polyoxometallate here. And on the other side, they insert the hydroquinone as a second redox species, which is oxidized on the other side. But during discharging, you have the opposite reaction. However, the system was run in water, and we know that if we try to push the potential to lower value, you can observe here that you have irreversible reaction, you have hydrogen evolution, and you cannot observe, so this is the same range that you can observe here, you cannot observe anymore the returning oxidation peaks. The system is becoming irreversible. One idea to overcome this issue was to mix together an organic solvent, which is miscible with water, in this case is dioxane, to stabilize the polyoxometallate. And in the mixture, 50-50 in volume of water and dioxane, you can observe also the returning peaks. So the system, the polyoxometallate, is becoming reversible. And the same, I also tried by using another solvent, the methyl sulfoxide. And also in this case, you can observe the returning peaks. However, this idea was coming as inspiration of my time in Camerino. In 2008, Pasqualina was doing her thesis, university thesis on this topic. She investigated different types of polyoxometallates, also phosphomolybdenum type and tungstenum type. and she tested these materials in different proportion of water and dioxane. And already she was observing that there is a stabilization effect of, especially of the reduced form of the polyoxametallate. And this was coming from the idea of Roberto Marassi to do this work. And several years later, I decided to take again this work in another context. The organic solvent can stabilize the polyoxametallate, but it's also very interesting to see that you have a shift in the, you have an expansion of the electrochemical stability window. This experiment was done in different electrolyte based on pure water or water dioxane or water DMSO on glassy carbonates without the polyoxametallate. And you can already observe that we can push to lower potential the hydrogen evolution here by gaining some potential window. And this is an effect that can be assimilated to the similar effect of a water in salt electrolyte, because we have interactions between DMSO and water which are stronger than water-water interaction. And in a similar way of water and salt electrolyte, we have less free water which can interact directly on the surface of the electrode, thus pushing the hydrogen evolution to lower potential. After this, I was building a supercapacitor by using activated carbon and activated carbon electrode on both sides. And I prepared an electrolyte containing polyoxametallate and another one without polyoxametallate. And as you can see, in the case of pure lithium nitrate in water and DMSO, you can observe a typical double layer square box voltammetry that you can see from the black curve. And when we have the polyoxametallate, you can see the superimposed multiple redox peaks. And when we go to higher scan rate from 5 to 100 millivolt per second, we can see that there is a very good retention of the shape of the cyclic voltammetry. That means that the polyoxametallate based water and DMSO system is very good also for a supercapacitor, so to be used with high power device. We also performed several charge and discharge experiments, and I will not go too much in detail of the experiment for sake of time, but I will show you the final result. The parameters of interest are obviously energy and power. And we can plot energy and power in a so-called Ragone plot. And you can see here we have the black curve represent the system without polyoxametallate. And when we add the polyoxametallate to the system, we can observe an increase in the energy for every power, both in the gravimetric and volumetric energy and power. And in this case, the maximum cell voltage was kept at 1.8 volt. We know that by increasing the potential, obviously, since the energy depends on the cell voltage, we can, of course, increase also the energy density, as you can see from this third curve here. However, it's very important to understand if the system under this condition, so 2 volt or 1.8 volt, is stable also for a long time. And therefore, we performed some accelerated aging, which was done under floating conditions. So floating means holding the system at the maximum cell voltage. And for supercapacitor, this is a way to perform an accelerated aging, because when we keep the our electrode at the maximum, at the limit, at the maximum voltage, the most part of the parasitic reaction occur. So here there is the representation of the 3 different situations. We have in the black curve the system without polyoxametallate, keep it at the floating potential of 1.8 volt. We performed this aging for a total of 300 hours, and every 10 hours we interrupted the experiment in order to monitor the performance in terms of capacity and impedance. And here you can see that the system without the polyox metallate show a decrease in performance with the floating time. And accordingly, we can observe an overall increase of the total impedance. When we keep the cell at the same voltage and we add the polyox metallate, we observe at the beginning one decrease and then a stabilization. And this also is reflected by the impedance, which show an initial increase, but then the impedance is remaining constant for the whole period of the experiment. Unfortunately, by pushing the cell voltage to 2 volts in the system containing the polyox metallate, we observe a rapid decrease. And after 100 hours, the system cannot deliver any capacity anymore. And we also observe a huge increase in resistance. Another important parameter to be checked in a supercapacitor, and especially supercapacitor with a redox electrolyte, is the self-discharge. Normally, after you charge the battery or supercapacitor, you don't use the device immediately, but you will use it after a certain time. And we need to check how much is the residual capacity energy stored by the system after this time. And what's happening when we have a supercapacitor with a redox electrolyte? We have our species which is reduced at this electrode, and the species which is oxidized on the other electrode can cross the separator and arrive to the other electrode, to opposite electrode, where you have the opposite reaction. And because of this crossover, we decrease, so we cannot keep the same capacity which is initially stored, and we observe then the self-discharge. What we did was to make this experiment. We charged our device up to 1.8 volt, and here you can observe the positive and negative electrode, which are monitored by a reference electrode, and we hold the potential for several hours, so 5 hours in this case, and then we let the system to relax and record the potential of positive and negative electrode here. And you can see that there is a drastic decrease in both cases of the potential. However, there is a mitigation effect in the case that we have the polyox metallate. And this could be attributed to the fact that the polyox metallate is able to strongly adsorb on the surface of electrodes. And this is something that was already proved before with other type of electrode substrates. I'm going now to conclude, and I want to highlight that starting in the group of Professor Marassi, we started to investigate the phosphotomestic acid as a catalyst for fuel cells. And after that, after several years, I decided to take again this topic in my group, and among different systems of batteries and supercapacitor. What I show you today is the first preliminary study of the use of this polyox metallate in a redox type supercapacitor. However, still there are a lot of space for optimization. The system is not optimized. We need another redox couple on the other side in order to have a better balancing of the system. And in order to prevent the self-discharge and the crossover of the species from one side to the other side, we can also think to work on the membrane. So here I just use the normal separator, but one can also employ one selective membrane which impede the one species to cross to the other side and vice versa. And I would like to thank the funding agency, which is the Ministry of Science, Research and Art in Baden-Württemberg, which supported this project, and my collaborator in Graz, so Turkamar Abbas, and Celeste and HIU and KIT, where I'm affiliated. And this is my group. So it was a picture taken during one of our last meeting. And finally, I would like to thank Professor Marassi and all the people that were sharing with me the period that I spent in Camerino. And thank you very much for your attention. Thank you.
Thank you, Sonia, for your very nice and interesting presentation. There is time for one quick question. If there is someone that has a question. I remind you that there is also a part of question and answer. If you want, you can use also this to make your question for the speakers. No one?
I have just a short question for Sonia. It's Rinaldo here. And
Hi, Rinaldo.
I know that polyoxymetallate has been used as redox mediator in lithium oxygen. Do you envisage any use in metal batteries in the future?
In metal battery, okay, we use it in metal ion batteries in at the moment. Sorry, maybe I interrupt the screen because I don't see you. Okay. Yeah, I think that could also be possible to be used in metal batteries as well. As I would say, they can be used as solid electrodes, so they can intercalate ions. So they can be used for sure for metal batteries, and also as redox electrolytes, also in a metal battery. Mm-hmm. This can be still one issue that I would have to say regarding the polyoxymetallate, that in this case we use that polyoxymetallate containing tungsten. Direction has to be taken in the direction to use metal with lower molecular weight in order also to increase the energy density, because they are a very big cluster and the molecular weight is also counting then on the energy density.
Hey, thank you.
Yeah, you're welcome.
Okay, thank you. We have to move on. And now I present Margaret Wolfram-Merens from ZSW that will present cathode materials, research and development of cathode materials for next generation battery. Please, Margaret.
Thank you very much for the introduction. I changed a little bit the title to Electrode Materials, but all the other things not. So, can you see my...
Yes, we see clearly.
Okay, fine. So, first of all, I have to thank the organizers to invite me to this symposium in honor of Robert Marassi. It's a big honor for me and also a big pleasure. And yesterday and also today, I saw a lot of people. We had collaborations in the past.
Margaret, please put in my presentation form.
Oh, sorry.
Thank you.
Yeah.
Thank you.
So now it's what happened. Okay.
Yes,
okay. I do not really remember when I first met Roberto Marassi, but I have known him for many, many years from his contribution to electrochemical conferences, in particular from the very fruitful and also stimulating discussions in the German-Italian electrochemistry meetings, which later became German-Italian-Japanese meetings, taking place in Germany, in Italy, and in Japan. And I think when times allows to travel again, we should resume this tradition and make a German-Italian electrochemistry meeting, and then we can toast to Roberto Marassi and have some fun together. I saw so many valued colleagues, and former co-workers and collaboration partners in this symposium that I think it's time to start new this Italian-German friendship in electrochemistry. Roberto Marassi was an excellent electrochemist, really coming from electrochemistry, which is not so normal this time. There are many people today having chairs in electrochemistry who are able to make a charge-discharge curve, but he was really contributed to a lot of fundamental work in electrochemistry, especially in fundamental investigations of the electrochemical kinetics, but he always taken care also of the application, especially in the development of materials and electrodes for batteries and fuel cells. And it is a shame that he passed away and that he cannot follow this tremendous change in the world related to batteries and fuel cells, also here in Europe. He always worked very carefully. He was a very enthusiastic researcher who was really liking excellent he was an excellent discussion partner, and he liked his students very much, and he also promoted his students by heart. I think sometimes he was very challenging, but he also encouraged his students and co-workers. And in person, he was a very calm, very friendly person, also a very modest person who never put himself in the spotlight. And he also was a very generous host. When I visited Camerino or when I met him, he always was very generous, and I really liked to work with him. I'm going to talk a little bit about research and development of electrodes material for next generation batteries. More or less 3 of my co-workers or former co-workers have a presentation here, so that all topics we were cooperating together are very well presented here, even better than I can do this. And I think Roberto was an excellent scientist, but he also was a very great teacher. I think there were some students or PhD students coming to Ulm. The first one was Marilena Mancini. First did some a phase of her PhD thesis in Ulm, and then she joined us as a co-worker, and she is now one of our most effective project leaders in ZSW. Second was Mario Marinaro. He gave his presentation yesterday. He is the team leader and now working on post-lithium systems. Then Sonja, who gave her presentation just a few minutes ago, spent some time in ZSW. She was awarded with a Young Researchers Group in a German program, what is not so easy as a non-German speaking person, and she's now a group leader at KIT. Then we had Marco Zecchiaroli and Silvia Calcaterra, who spent some time of her PhD thesis in ZSW, and last but not least, Gilberto Carbonari, who works in ZSW and who is working now on impedance analysis of complete batteries and cells. We had nearly 15 years of fruitful collaboration with many topics which are covered here in this symposium. And this is our last common publication from the work of Marco. And when I saw the title 1 week ago, high energy and high power lithium batteries and the materials, lithium titanate activated carbon and lithium vanadium phosphates. This are exactly the topics we work together on here in more or less in one combined in one paper. And also the dedication, I want to read it. This work is dedicated to the memory of Professor Roberto Marassi, to thank him for his passion and his immeasurable contribution to the research in the electrochemistry field. He also instilled love for electrochemistry to his research group and his students. And I think that especially the last point, that he really inspired his co-workers, trained them very well, is one of the highlights of Roberto Marassi, and I think all his co-workers have made their life in business and in their private life. We started on in mid of the about 2026, 27, we started to work together on mesoporous titanium dioxide for high rate performance and especially also for fast charging, which is still a topic today. Started the beginning with anatase titanium dioxide, then went to rutile titanium dioxide in order to improve low temperature performance of lithium-ion batteries, fast charging ability, and also discharge capability. And of course, titanium dioxide is also a cheap and environmentally friendly material. Was possible to achieve excellent rate capability and also very high cycling life and a very safe system with no lithium plating. But unfortunately, all the world focused only on energy density, and lithium titanates and titanium dioxide have a lower energy density compared to graphite or silicon, and therefore the interest in titanium oxide based batteries was reduced during the last years. But I think this is an excellent system for high rate capability and also fast charging. I want to show you this slide here, the plant cell production in Europe. There is a very dynamic growth driven by the automotive market, and there are many announcements of installing gigafabs of battery production, including a company in Italy. And I'm sorry for Roberto Marassi that he cannot see how this field has developed. For when he worked on batteries and he really believed in this energy storage system, more or less all the batteries were made or produced in Asia. But times are changing, and I'm convinced that we in Europe together can catch up with the Asian companies and will be able to develop something superior in the future. There's a roadmap for the cathode materials to have high energy density, safety, and sustainability. In principle, there are 3 different classes of materials which are quite promising for high energy systems. These are the layered oxides coming from the lithium, nickel, manganese, cobalt oxide. And here is a shift in composition to more nickel-rich materials, and the development goes to reduce completely cobalt from this layered oxide. But this nickel-rich materials have one challenge. This is the instability in the charge state and the loss of cycling life if you go to higher nickel contents. Then there are more manganese-based materials. The base material is lithium manganese spinel, which has been abundant for the specific energy is too low, but there is the option to go to higher voltage materials, to high voltage spinels, which have better specific energy and also energy density. These are quite high rate materials. Challenge here is the electrolyte stability window and the degradation at high temperatures. And then there are other concepts to extend the redox chemistry using manganese-rich or lithium-rich materials with different structures, including the oxygen redox pair. This material show quite high energy density. So the increasing demand for material also raises problems with the sustainability of the material. On the first hand, there is a shortage in cobalt, but maybe in the future there will be also a shortage in nickel, especially if we go to this very nickel-rich materials, which lead to a quite high demand of nickel material, and going to more manganese-based cathode material would really solve these problems. And last but not least, there are also some concerns about lithium. Therefore, also alternative systems like sodium-ion systems, or maybe in the future magnesium and calcium systems are under development. Battery materials, this is more than only a chemical composition. To get high energy density, good rate capability, and stability, these materials have to be optimized along the whole chain, from the chemical composition up to particle size distribution, particle architecture, and also the processing to electrodes to get electrodes with high porosity but also high density is very important, and this is a topic for materials development. So let's have a look on the different cathode material. At the moment, there is a strong demand for nickel-rich material going from NMC 111 to more or less nearly pure lithium nickel oxide. The challenge is the stability of the material and also the synthesis of the material for this materials lead to lithium nickel exchange in the structure, which leads to higher irreversible capacity and also an increase of resistance. This can be seen here from the slide that with incorporating nickel in the lithium position, we get some collapse inside the structure, which blocks the diffusion pathways for the lithium and lead to higher internal resistance and a lower rate capability, and also to a higher first cycle capacity loss. There are different options to stabilize this material. One obvious option which has been selected in the past was to make mixed oxide with cobalt. Now we have to face the problem that cobalt is not a very sustainable material, and that this nickel-rich material should be cobalt-free. And there are other options which are known also for a long while. For example, doping lithium nickel oxide with magnesium. This was also a direction Roberto Marassi has followed many years ago. There are some publications on magnesium doped lithium cobalt oxide, but also about measurements of the kinetics of lithium nickel oxide, lithium cobalt oxide, and also doped lithium nickel oxide. And now we see a renewed interest in doping of nickel-rich materials with magnesium, aluminium, titanium, or also with tungsten or other elements. There are also some secondary effects for nickel-rich materials on the structure, on the surface of this material. We have to be sure that these materials are have been washed and surface protected. This is also a research topic for investigating the not SEI layer, but the cathode electrolyte interface to avoid increase of resistance and to avoid defects on the surface near structure in the lithium nickel oxide. There are different directions to improve this nickel-rich material by washing and surface treatment. And meanwhile, some of these materials are very stable and also give very good rate capability, even on prolonged cycling life. There's another material, this high voltage lithium manganese nickel spinel, which has no residual lithium. And if we look at the demand for raw materials, high voltage spinel is a very attractive material, for it's not only cobalt free, it also has a low nickel content, and it's possible to add an additional lithium into the structure. Also here, the composition of the material is just one of several contributions to the performance. Also here, optimizing primary crystallites, particle morphology, particle size distribution is very important. Also to have a very low surface area to avoid side reactions with the electrolyte. Together with Roberto Marassi, we were involved in a European project from 2010 to 2013 for the development of a high voltage lithium nickel manganese spinel full cell, where at ZSW we made the materials development for the cathode material. At the University of Roma, the development of the anode, in this case carbon tin, and the electrolyte, also a Swedish university was involved. And Roberto Marassi's group were working on impedance analysis and testing of the full cells. At that time, it was 2012. We delivered, from our point today, a quite lousy single layer pouch cells. You can see on the left side that this cells lose capacity capacity with increasing current. But also here we were able to make a relatively, for this time, relatively stable system. And Roberto Marassi gave us some directions how to improve the material. And some years later, we were able to develop a high voltage lithium manganese spinel with quite good cycling stability, also in the fuel cell, and also with very good rate capability. By surface modification of the spinel with lithium niobate coating, and we are now working on other surface modification. For lithium niobate is also not the most sustainable and cheapest material. So in order to increase further on the energy density, this is to use the high voltage plateau and the additional capacity of the lithium nickel manganese spinel. We can insert one more lithium inside the structures, which leads to very high specific energy, if it's possible to use this additional capacity. But there's one point: the higher the utilization of the material, the higher the capacity loss over cycling. You can see here, if you cycle only on the 4.7 volt plateau, the material is very stable. If you go to 320 milliampere hour per gram, which is near the theoretical capacity, the cycling stability is quite low. And in the high voltage plateau, we are working even beyond the electrolyte stability window. So we had a closer look to this low volt region. This was also the work from Marilena Mancini in our group, who studied the structure of the low voltage plateau, and within the structure there is a complete mixed series of the cubic and tetragonal phase, and there is no reason why we should observe different plateaus inside the discharge curve.
Margaret, you have only 1 minute just to finish. Yes.
Yeah. Okay.
Please.
So at the end, we found out that this plateau is kinetically influenced, and by proper adjustment of the particle and crystallite size, we were able to design a material which gives a quite high capacity of more than 200 milliampere hour per gram, and the length of the plateau is controlled by the crystallite and not the particle level. These are the results of half cells which work very well. This topic has been already presented by Sonia. Another inspiring proposal we got from Roberto Marassi was to work with aqueous binders. We now work with aqueous binders for cathode material, and his inspiration is going on. These are some of the results of his students, of his former co-workers in my group. And unfortunately, I had only this photograph. This is the wedding from Marilena. I had no other photo with Roberto Marassi. And I thank him very much for his very inspiring discussions, and also for the nice co-workers I have now in my group. Thank you very much.
Thank you, Margaret, also for your presentation and for these nice words. And I am sorry, but I have to go ahead because
I was too long. Sorry.
We have a little bit of delay. So, yes, I invite everyone who has a question for Margaret and also for the other speaker to use the question and answer tools that you find on the left, on the right of your screen. Now, I would like to introduce Paweł Kulesza from the University of Warsaw, and the speaker is on electrochemical and photoelectrochemical approaches to energy conversion and charge storage. Please, Paweł.
Is it?
Yes, we can see
okay, now?
The presentation. Perfect.
Okay, thank you very much. First of all, it's my great pleasure to participate in this meeting. Many thanks for invitation. And of course, it's for me personally important meeting because, I know Roberto since 1993, since my first visit. Actually, since 1992, when he was visiting University of Warsaw, and then started to talk to me that he's very interested in Prussian blue and related systems. And then his story started. Today I will talk more about electrocatalysis, since my research went more towards this direction, but I will try to refer to some old work too. So if I summarize the present research, it covers development of hybrid materials. And I'm also interested still in oxygen reduction, which we actually started to do together with Roberto Marassi. Also in alcohols and, let's say, fuel cell type research. A lot of effort, which I will not talk too much today, but I will mention. Concerns photo electrocatalysis and water splitting, and also carbon dioxide reduction, which seems to be probably my major research area. I'm interested in capacitors. Roberto was not very keen on capacitors at that time, but I will also say a few words related to this. So if we go to the solid state materials Prussian blue type systems, to make them effective in charge propagation, I would like to say that we need to meet certain requirements which are summarized by Ramsden-Duff equation. It means we need to have a high concentration of redox sites, short distance, and high self-exchange rate. And of course, the counter-ion motion is very important. And most of Prussian blue analogs with potassium meet this requirement. We started together with Silvia Zamponi, Mario Berrettoni, later Marco Giorietti joined the research. And we have very many important publications. It is history, but well-cited history. And many thanks to those people for very nice days together. So Prussian blue is very well known. Probably one of the oldest coordination compounds. We still teach students about Prussian blue, and there's a lot of unknown features and very important chemistry. Important is self-exchange and also pseudometallic conductivity in partially oxidized Prussian blue. We are more interested at that time, and we pursued this research further with some analogs of Prussian blue, like nickel hexacyanoferrate, where you replace one of the irons with a different metal. And the counter-ion motion is quite important. Nickel is more layered type system, I would say, resembling more clays than zeolites, and is extremely fast in charge propagation. So electron transport accompanied by electron accompanied by motion of counter-ions. Diffusion coefficients are moderate, so we were aware that we will not break through in certain applications, but for sure, definitely, as was demonstrated in recent years, is for charge storage. But now we'll go to something which was not started with Roberto and the persons I mentioned, but we later, actually Iwona Rutkowska from our laboratory, pursued research on using nickel hexacyanoferrate as a charge relay mode redox mediator. At that stage, we used mixed valent because there were two irons at two oxidation states. Well, the simple experiment would put into the between two slides like a sandwich configuration and go back to the old electrochemistry. Roberto was great, he knew everything, old and new. He's an extremely great mind. I really enjoy the time and all the discussions. I will mention this later, but not only scientific, but also social and political. But of course, we can use a number of systems, sandwich configuration, interdigitated arrays, the same principle, cardinal principle, two electrodes. You have had two processes on two electrodes, so you can nicely investigate. Now, there are many systems. Royce Murray developed, for example, gold covered, and many, many others. So the good charge relay gives you a reversible peak around the zero if you use potential difference instead of three electrode system. And it was strongly dependent on the degree of hydration. I remember with nice weather in Camerino during the old days, it's also nice now in summer, you know, the system could evaporate very fast and go from the nice reversible peak to the straight line. So it was very interesting. 50-50 iron 3 to iron 2 gives you very high current, maximized currents. So we went to the dye-synthesized solar cells, actually the work of Iwona Rutkowska. And metal hexacyanoferrate in mixed form could serve as a redox mediator and help upon injection electron to the conduction belt of titania covered with a dye, we can make a cycle by using redox mediator. And the crucial part, interesting, is that nickel hexosanoferrate has a relatively positive potential, much more positive than iodine iodide couple commonly used in the systems. And if you look on the scale, we are more positive, so the potential output coming from this type of system should be better. And indeed, it was. And the mechanism is similar to the iodine iodide couple because we actually reduce oxidized dye using the iron 2 cyanoferrate part. And we can regenerate the system upon illumination. So we basically speaking can go to pretty high potential output. It was not great, perhaps, the current density, at least it was done a number of years ago, but the potential output was better than for the iodine iodide system. Of course, this research is more fundamental than practical because it's difficult to control the degree of hydration. Capacitors. I will not talk too much after the very nice talk of Sonia, but I would like to say that capacitors could be done. We are interested. Actually, Magdalena Skunik-Nuskowska, she is going to collaborate with Sonia, and she's very interested in our laboratory in this research. We were more interested in building something hybrid between the true capacitor and pseudo-capacitive systems with redox couples. But at this stage, I will give an example which will probably Roberto would like a lot, because we combined a capacitor. It was a part of work of Magdalena with Anders Hackfeldt and Nigula Hopoulos from Sweden at the time, not from Lausanne. So the left part is a photocell disynthesized. The right part is a capacitor. I would say capacitor with ruthenium oxide. Quite expensive capacitor, but military and some expensive cars, they use it. And we can charge using the light, and we can discharge using the capacitor. So if I look at the disynthesized solar part, we use a relatively not very efficient photocell, but we use a completely solid system with a conducting polymer, which is a whole conducting system. It's not as efficient as iodine couple or nickel hexosanoferrate, but it works in solid state. And on the part of the capacitor part or pseudo-capacitor part, we use a ruthenium oxide system, which is a very effective system, it's well known. And combining less effective system with very effective system sometimes works in favor of both. And indeed, depending on the light you can charge, you can also observe change of the potential. Obviously speaking, the better light, better sun, like in Camerino in summer, would work great. And of course, discharging depends on how much time you need it and what current you use for discharging. Briefly speaking, the Coulombic efficiency was on the level 70%. Please remember, it is an electronic type device. Everything is a single system. Use of silver is not optimized, but it's interesting. So from one side, we use a photoanode, we charge the capacitor, and discharge is through the external counter electrode and inside counter electrode of silver. It's a quite smart system, but it also shows that we have interest in, I would say, combination of photoelectrochemistry and capacitor. So important observation is that you can build electronic devices. Perhaps you know the solar efficiency is not very great, Coulombic efficiency is much better, but at the time we are talking about renewable systems, energy resources is interesting research, but rather fundamental at this stage. Let me go back to the hydrogen-oxygen fuel cells, because in fact, most of our collaboration with Roberta is very interesting because we are operating parallel. I got involved in oxygen reduction project, actually coordinated by the German foundations and by Ulm. And at that time, Roberta was in a project in Italy. And we started together work on oxygen low temperature fuel cells. And if I go back to the older research, it's well known we don't want hydrogen peroxide, we want 4-electron reduction. We can get a much better potential and, of course, better stability. At that time, we are working on nanoparticles modified with polyoxymetalates. We use for different purposes. It was actually part of the research also of Małgorzata Chojak, who visited University of Camarino at that time as a graduate student. Later, other people were coming and pursuing research at both institutions. I don't need to talk about polyoxymetalates, but we can certainly prove the presence on the surface using FTR. And at that time, we'll say it's nothing special, but today, but that time it was interesting that modification with polyoxymetalate shifted the onset potential. It was very interesting for us. Why? We know now also from XPS that there are changes electronic, but even visually, we see that the oxidation of platinum was shifted toward more positive potential. So in a sense, the potential window of metallic platinum was extended. That was the reason going to the classics. Actually, Roberto liked classics, and it was actually his very big advantage in understanding science. Experiments done, this was done in Camarino. We see in a gas diffusion electrodes that we have improvement when we have platinum nanoparticles modified with polytungstens. Well, the next part, it was a period where people believed more in methanol fuel cells. The reason was that it's easy to handle liquid fuels. So ruthenium selenium systems, ruthenium modified on the surface selenium is like cheating in a sense, because we make ruthenium much more metallic as a corrosion protection. So at that time, we also worked on ruthenium selenium. We had samples from different sources, both from United States, from Germany, and from Italy. And we modified them with tungsten oxide. We believe that it was a little bit more stable than polyoxymetalate on the surface. And it was indeed shift in the reduction potential for the oxygen reduction. And the amount of hydrogen peroxide decreased. The system was never as great as platinum, even not optimized platinum, but the ruthenium selenium was not optimized either, but the results were quite interesting. Well, when we did experiments, actually it was also part of collaboration with Andrzej Więckowski and Adam Levera did with Wolfram Jägerman experiment together, showing that there's no change on the ruthenium side, but there's a change on selenium side. Selenium is becoming more, if you can say, metallic. Also, it's not a metal in a sense, but in a very small amounts, it behaves more like metal. So in a sense, we are making indirectly ruthenium more metallic. And there was also improvement in a fuel cell using ruthenium selenium. So this was done actually in Camarino, that experiment. Oxygen reduction is a topic which I pursue under different conditions with different collaboration. Nowadays, there is a big project, AET raw materials, headed by Professor Vito Di Notto. And I'm part of this, and I'm also very happy to this. As you see, I have very close links to Italy. So we use reduced graphene oxide. In fact, it was a part of the Horizon 2020 first. And reduced graphene oxide is an interesting system. It's something between oxide with a lot of groups on the surface and, let's say, inert graphite. So it is more hydrophobic than oxidized graphene oxide, and less hydrophobic, and lower hydrophobicity makes it more stable on the surface. The problem of the support is extremely important because carbon black is not very stable under practical conditions. So we are looking for different combinations of the systems. There's a lot of work done in this area, but I would like to mention only about one part, about adding traces of iridium. It goes back a little bit to the concept discussed with Roberto that we need to do something with hydrogen peroxide. Iridium is a very good catalyst. for the decomposition of hydrogen peroxide, much better than the catalyst for the oxygen reduction. We can put traces, small amount of iridium, as you see, very small particles, and indeed you shift potential and you decrease formation of hydrogen peroxide. The system was bifunctional or bicomponent in a sense, because iridium was on graphene. In fact, that graphene was even stabilized with some small amount of silica, but platinum was on carbon nanotubes. Later, we learned that also a combination of graphene, reduced graphene oxide with carbon nanotubes is helpful, at least from the theoretical point of view. I will not talk too much about this, but I would like to mention, showing that in the right corner figure, that decomposition of hydrogen peroxide starts very early on iridium. Basically, at the moment it appears, iridium helps. Of course, iridium is very expensive, but there are some information. There is some information that that one is added by Japanese in very small amounts to their cars. We are not aware of this when we are doing this. Going to fundamentals of electrochemistry, if you accelerate the second reaction, decomposition of hydrogen peroxide, you can even shift the potential. Classics, electrochemistry of 60s. Roberto also knows it very well. Okay, we worked with methanol and ethanol with Roberto too. There was a period that people believed that ethanol is a fuel. They still believe, but there are some fundamental problems to be resolved. Ethanol is difficult to handle because you have to break CC bond. There is not such a problem in methanol. In methanol is a problem like in all small organic molecules of poisoning with carbon monoxide. So to make the system effective, 12 electron, you need, basically speaking, to search for very good catalysts. So we also started this research, parallel in Warsaw and parallel in Camerino. We are considering different bimetallic particles. We are modifying them with Poliox Metallating. It was a question not only of stabilizing, but making them better distributed on the surface. Remember that Poliox Metallates are superacids, and it also improves the mobility of protons. It is very often also an imitation in fuel cells. I know that people that were adding at some time, and I remember the research done also in Italy, in some institutes, that they were adding Poliox Metallates to fuel cells to improve proton mobility. And this is the case. In all cases, briefly speaking, all catalysts, we are getting improvement. Of course, Poliox Metallates as a monolayer are not very stable. We know that using XPS measurements, that basically speaking, there is not too much change on the platinum side by adding Poliox Metallates, but there is a change on tin part. Tin is a second component which helps with decomposition of carbon monoxide. With ethanol, platinum tin is probably a better catalyst because it is a heterogeneous alloy, and platinum can work separately and tin can work separately. Platinum also breaks the CC bond. Now we see clearly from this that we have more tin oxide once we modify the system with Poliox Metallate. So tin oxide is actually active in removing the poisons. So changes in morphology, basically speaking, we still cannot exclude interactions of Poliox Metallates with platinum, but there is a problem of stability. And it was very nice because Roberto found, once we are discussing and enjoying great Italian wine and very nice atmosphere, which I go back very often, and at his house, with many thanks to Licia, his wife, she really introduced a very nice and kind atmosphere during all my visits and all my stays in Camerino. But once discussing, we mentioned the old work by Misono in Italy, that there are cesium and rubidium salts, which are not soluble, but they keep the high proton mobility of Poliox Metallate structures, and they are zeolitic in nature. We build systems, very small catalysts. I don't have time to talk about details, but in fact, the fuel cell operating, it was later done.
1 minute left.
Okay, I'm finishing in 5 minutes. This was done by Artur Żurowski, he completed PhD in Camerino, but I was also a co-promoter, co-research director, formally and realistically of this research too. Problem was that still we produce more acidic acid than carbon dioxide. We improve efficiency, but still is a problem related to this. Later we use mixed oxides of tungsten, oxide, and zirconia, highly protonically conductive. We can remove hydroxyl groups, and added rhodium, which breaks CC bond, and briefly speaking, we can observe enhancement. The model is that rhodium can break CC bond, but the actual reaction is continued on platinum ruthenium. This was done by Ivona Rutkowska's laboratory later. Let me go back last 3 minutes of my talk, carbon dioxide. We are heavily interested in this. Well, I didn't start with Roberto, this research, because at that time, he was involved more at the end of his career, more in charge storage and batteries. He discontinued electrocatalytic research to a large extent. But there are many problems of carbon dioxide reduction, in addition to high overpotentials, necessity of activation of the molecule, competitive hydrogen evolution, very inert system. We are interested in building electrolyzers too. And it's very interesting that we can, this is a typical example. The reduction is basically dominated by hydrogen evolution. It would be nice to do it in acid medium because the systems use membranes. And carbon dioxide can be adsorbed on the surface and reoxidized, but only interfacial phenomenon. Bulk carbon dioxide will not be even on copper electrodes. Because copper we generated for copper 1 oxide, to make it clear. Using tungsten oxide, briefly speaking, which has some activity because tungsten oxide forms hydrogen-rich bronzes. And these are active, but together with copper, which was electrodeposited, excess was removed. We could observe a very nice situation. So we produce more or less 50-50 hydrogen and reduce carbon dioxide. Later, we know that this reaction went to methanol. So in a sense, we are pursuing at low temperature, Fischer-Tropsch type reaction. We can determine product going back to the, Roberto liked electroanalysis. And I'm sure he would like to see that you can use rotating this electrode for different purposes. Well, we developed systems also for the water splitting. I will skip this part and use gold nanoparticles modified with Poliox and Metallates because, if it's going to be work, we can make a semi-photo, semi-conventional system. I will skip this part and go to the end of my talk. As you see, there are a large number of people working on this research. But I always put Roberto as the first point, as a collaboration, because we really did a lot together. So, of course, I should thank also the granting agencies. And at the end, I would like to remind about the special issue of Journal of Solid State Electrochemistry, which will be devoted. The deadline is extended thanks to Fritz Scholz, editor-in-chief of the journal, but please try not to be too much late because we have to eventually publish it. Thank you very much for your kind attention.
Thank you very much, Professor Kulesza. And also in this case, we have no time for question. And so if you have some question, please use the question and answer tool. And I move immediately to the flash presentation. I remember that there are 5 minutes for each presentation, so please keep in time. And the first one is from George Bosch from Karlsruhe Institute of Technology. Please.
I cannot share.
Okay, I don't know. I have not the.
I'm working on it. Yeah.
Okay, thank you.
Okay, now you should be allowed.
Yeah, now it's working. Okay.
Okay.
Can you see my screen? Yeah.
Yes.
Okay. Hello, everybody.
George, just one thing. Are you sharing the presentation or the screen?
The screen.
Screen? Okay, so it's fine.
Okay.
Okay, you can go on.
Again, hello, everybody. My name is Georg Bosch. First, I want to thank the organizers for inviting me to present my work with the title Hybrid Electrode based on Poliox Metallate Activated Carbon for Electrochemical Energy Storage at this conference. The motivation was to combine a long-distance driving and fast acceleration in one hybrid material, which then provides the fast electron storage, hybrid capacity, high capacity, and good stability. Therefore, polyoxymetalates and activated carbon were chosen. Polyoxymetalates are stable against oxidation and reduction reactions and can absorb and release up to 24 electrons in fast and reversible multi-electron reactions. On the other hand, activated carbon can act as a supporting material, which has a high inner surface, high absorption properties, a good conductivity, a low weight, and also double layer capacitance. The hybrid material can combine the positive properties of both materials and negative properties of polyoxymetalates, like their good solubility in polar electrolyte and weak conductivity, can be compensated. The fabrication process consists of a repetition of dispersing and filtering and the washing, which makes it a simple synthesis. It is well known that polyoxymetalates can include a high number of structural water and that this can have a negative effect on the non-aqueous batteries. But due to the high thermal stability of the pure polyoxymetalate material, it can be tried at air by heat treatment. The hybrid material consists of activated carbon, which will decompose by heating at air, but also heating with inert gases leads to a decomposition of the polyoxymetalate cluster. This leads us to the treatment in vacuum, where activated carbon and polyoxymetalate stayed unchanged. The green XRD pattern shows the reflexes of the pure polyoxymetalate material, which can also be found in the blue pattern of the hybrid material and confirms the stable structure. Compared to the SEM picture of the pure polyoxymetalate particle in the front with a diameter of around 250 nanometers, the hybrid materials show well dispersed polyoxymetalate particles on the activated carbon with particle size of around 10 nanometers, and thermogravimetric analysis show a composition of 57% of activated carbon and 43% of polyoxymetalate particles. Compared to the untreated polyoxymetalate, the cycling stability could be increased in literature by heat treatment. And the combination of polyoxymetalate and activated carbon in a hybrid material leads to a further increase in capacity, and the capacity retention is comparable to the pure polyoxymetalate material. It can be concluded that the hybrid material is sensitive to inert gases during heating. The particles could be distributed well on the activated carbon, and agglomeration could be avoided. The small particles and the high distribution leads to an increase in the capacity, and the cycling stability is comparable to the pure polyoxymetalates. Thank you for your attention, and these are my acknowledgements.
Thank you very much also for being in perfect time. So I have to go ahead with the next speaker, that is Marzena Krech from the University of Warsaw. Please, Marzena.
You see the presentation?
Yes, it's starting. Yes, you can put as presentation.
Yeah, I shared my screen. Can you see it?
Yes, the screen is shared, but you have to start the presentation.
Okay.
Yes.
Here I
Perfect.
am. So thank you for the invitation. My name is Marzena Krech, and I would like to tell you about cobalt hexacyanoferrate modified titanium-based solar side catalytic systems for oxidative water splitting in acid medium. So at the beginning, I would like to tell you about metal hexacyanoferrates, which are metal substitute Prussian blue analogs. And they have a cubic structure in which metal, for example, cobalt ions, are surrounded by nitrogen-carbon ligands, and the iron ions are surrounded by carbon-nitrogen ligands. This structure is often distorted. It means the octahedral coordination, for example, of cobalt ions by nitrogen-carbon ligand is not complete and may involve hydroxyl groups and result in catalytic properties. These compounds have zeolitic character and only ions of appropriate size, example having catalytic properties, can fit into the channel. This graph shows difference between measuring cobalt hexacyanoferrate in two different environments. And upon medium transfer to acid medium, redox transitions are largely suppressed due to the absence of charge compensating potassium cations, but some potassium stays in the structure. Possible forms of fully oxidized systems of fully oxidized cobalt hexacyanoferrate include also structures containing potassium and catalytic cobalt in zeolitic channels. These structures are confirmed by Raman spectra shown on this slide. And for the oxidized forms in acid medium, which is the green curve, the signal at about 2,200 replicator centimeters undergoes splitting. It's from the strong interactions with both iron and cobalt ions, predominantly at +3 oxidation state. The signal at about 200 to 300 centimeters under replicator centimeters implies existence of cobalt oxo or hydroxyl species. This graph shows oxidation of water to oxygen at cobalt hexacyanoferrate layer in sulfuric acid at potentials higher than 1.3 volts. This graph shows oxidation of water at ruthenium nanoparticles and cobalt hexacyanoferrate modified ruthenium nanoparticles. Performance of both system is identical, but its stability of the modified one is much higher. Over here, I presented a comparison of catalytic activities during water oxidation. And as it's shown on the graph, hexacyanoferrate system is less active than modified system, but it's a noble metal-free system. It can be used to stabilize of highly active but otherwise unstable ruthenium oxides catalysts. For the conclusions, the cobalt substitute Prussian blue analogs have electrocatalytic properties towards oxidation of water to oxygen, and the cyanometallite system can be used to stabilize highly active but otherwise unstable ruthenium oxide nanoparticles without diminishing their catalytic reactivity. Thank you for your attention.
Thank you, Marzena. And now we move on, and we move to Christina Pfeiffer from Karlsruhe Institute of Technology.
Hi.
Please, Christina. Hi, you can share your presentation.
Yep.
Sorry, your screen, not your presentation.
Do you see my screen?
Yes, we see your screen. Yes, you have to start the presentation. Perfect.
Okay, great. So thank you for inviting me to this conference. Today I want to speak about my PhD work, which I was doing in Sonja Toke's group. And my topic today will be the reactivity and interplay of critical...
Excuse me, Christina.
Yes?
I think you're... okay, now it's coming. It's great. Sorry, there was a delay. It's fine.
Okay. So, yeah, this is my topic of the talk today. Reactivity and interplay of critical components in sodium-ion batteries. So, as we all know, the Nobel Prize was just given to these three men here for the lithium-ion batteries. So the main question is, why do we need alternative systems if we have a pioneering one? And mainly the reason for this is that the application of solely the lithium-ion battery will lead to a shortage of supply, and therefore we need alternative technologies, especially for stationary applications. In the state-of-the-art literature, the sodium-ion battery is so popular because the properties of lithium and sodium are very similar. And that is the reason why the researchers hope to accelerate the development of sodium-ion batteries by knowledge transfer. The problem here is that we use, for example, a 3-electrode cell setup to characterize active materials, and the counter and reference electrode are always the corresponding alkali metals. We know that lithium is very stable in the commonly applied carbonate-based electrolytes, which are shown here, like these different carbonates with the respective alkali metal salt. But in the literature, the enhanced reactivity of sodium was mainly neglected, and the electrolytes were just taken over from LIBs with the respective sodium salt and sodium metal as counter and reference electrode. That's why, because the enhanced reactivity of sodium, we tried to find out if it has a difference or if it has an effect. And what we saw was a drastic change of the electrolyte when placing sodium inside. And that means that the results you get from these measurements are not reliable. Nevertheless, we were able to stabilize the sodium metal in the different electrolytes by either adding FeC to the carbonates or replacing the carbonates by D-glyme. Still, we have to find out how these electrolytes behave in an electrochemical cell during cycling. And we did this by using a material with a very complex electrochemical behavior, antimony oxide. And by doing so, by cycling this material in different electrolytes, we were able to investigate the influence of the electrolytes on the sodium metal and on the working electrode. And what you see here is mainly that in the case of FeC, we get a very good stable electrochemical behavior, whereas when we use D-glyme, we get very irregular values of the capacity, even if the electrode doesn't look so much affected. And this is because D-glyme can dissolve the active material. So the sodium metal is stable, but the active material is affected. And that brings us to the conclusion that FeC containing electrolytes are appropriate to be used in cells which contain sodium metal, and they also stabilize the working electrode. So the next thing we looked at was the influence of carbon on antimony-based electrodes by using the knowledge we had before, so using the FeC-based electrolyte. And what we see here is that the carbon really affects the performance of antimony-based electrodes. So depending on the chosen carbon, the rate capability and the performance can be really altered. That means that choosing the right carbon is of vital importance because it gives the possibility of better conductivity and superior SEI features. So overall, in general, my work gives a guideline how to reliably transfer results from one battery system to a similar battery system. It shows how important it is to consider the influence of each component, but also what to do if the transferability is not guaranteed. And in the end, the work gives ideas how to approach issues to find the way to an optimized battery system. Thank you.
Thank you very much, Christina. And we move on now to Kinga Zduniak. I hope that I pronounced well. From University of Warsaw.
You can see my presentation.
Yes.
Okay.
Yes.
Good morning. Thank you for your attention. Today I tell about chronocoulometric approach to elucidation of mechanism of oxygen reduction reaction. And in this slide, you can see voltammetric reduction of oxygen at Vulcan-supported platinum nanoparticles. The red line presents background current in absence of oxygen, and the blue line presents reduction of oxygen. For either electroreduction of oxygen, we need 4 electrons, and we want to decrease formation of hydrogen peroxide intensity. Because while using voltammetry, precise numerical description of the catalyst process is difficult, we can chronocoulometry propose here, and the reduction of oxygen takes place on the metallic platinum, which is formed as a result of the reduction of platinum oxide. And I applied a pulse between 1 volt and 0.5 volts. And studied the process of oxygen reduction with chronocoulometry. And this slide we can see typical gap potential step chronocoulometry. This method matches the dependence of the charge of duration of the electrode process at a constant potential. Negative sign because reduction is a forward step. Here we observe charge equivalent to reduction of oxygen together surface process, and the next we observe reverse step, and this is oxidation of hydrogen peroxide with a surface process. And this slide presents separation of surface phenomena from bulk reduction of oxygen using Anson plots. For the beginning process, we observe not Faraday portion, for example, double layer charging or surface hemisphere. We can see that the curve is not linear. After we observe linear portion, after we observe linear dependence, and it is the reduction of oxygen, and the reverse step, it is oxidation of hydrogen peroxide. And this slide illustrates diagnostic experiments. We can see quadratic equation. The first part, it is diffusion, but the second 2DL, it is double layer charging reflects the catalyst peroxide. And the third, this is charge related to the charge of electroactive surface space. And the second and the third, this is not diffusion part. On the right side, you can see concentration, diffusion coefficient, and slope for full electron oxygen reduction in the acid medium. And for the linear portion, we calculated the slope, and it is ideal. On this slide, I presented chronocoulometric response for Vulcan-supported platinum nanoparticles in oxygen saturated. Vulcan-supported platinum nanoparticles is a model catalyst, and we observe a reduction of oxygen process, and it is oxidation of hydrogen peroxide process. For this tool, we can see oxidation reduction charge, and we calculated slope. And on the basis of chronocoulometry, we have calculated the following parameters: effective number of electrons involved in oxygen reduction, and the percentage amount of hydrogen peroxide formed during oxygen electron reduction. And the results of chronocoulometric estimation are consistent with our calculation based on rotation ring disk electrode, voltammetric observation, and the Vulcan-supported platinum nanoparticle is modern catalyst. And my conclusion, the determined number of electrons participating in the oxygen reduction reaction indicates the efficiency of the process, and the double potential step chronocoulometry permits estimation of the effective number of electrons, involve the oxygen reduction and fast diagnosis of formation of hydrogen peroxide intermediate. Thank you for your attention.
Thank you, Inga. I don't know if it is my device or the overall communication. We missed something at the end, but we thank you in any case. And not least, Paulina Krakova from University of Warsaw.
Yes, so everything is okay? Can you hear me and my presentation?
Okay, Paulina, you can start.
Yes. So thank you for your introduction.
Yes, we see.
Paulina Krakówka, and today I would like to show my presentation about best results which I achieved from my latest research. And today's talk will be about rational metal oxide based time electrocatalytic reduction of carbon dioxide. My interests concern development of systems for the electrocatalytic reduction of carbon dioxide in nimne-ultra media. Of particular interest to the preparation of advanced catalytic materials is efficient utilization of catalytic sites, metal and metal oxide nanostructures, their stabilization and intentional activation, as well as organization into two-dimensional arrays, ultra-thin films, or three-dimensional networks on electrode surface. They can form nano-sized materials with well-defined composition, structure, and thickness that exhibit desirable electrocatalytic properties. Iron oxide is used in many industrial chemical processes. An example of an iron-containing catalyst is porphyrin, which is an example of a metal with a microcircuit ligand. We came up with an idea to use iron oxide and check how the CO2 reduction process goes. In literature, we have information that this process goes with low evolution of hydrogen. We can get intermediate product like carbon monoxide or formic acid. And there is a possibility of partial reduction to catalytic iron zero oxide states. It turned out that in the case of iron oxide, the reduction process begins at more positive potential. For a two-layer system, we will observe a synergistic effect and enhancement of net CO2 reduction current. And if we take a look at just bare nanoparticles of iron oxide or bare zirconium nanoparticles, we will see that these two components together are giving much better results and better selectivity. Moreover, I explored here the ability of polynuclear inorganic metal oxo systems to stabilize and functionalize metal, for example, copper or iron nanostructures. Here, certain nanostructure of metal of tungsten or zirconium have been demonstrated to influence support metal centers in ways other than simple dispersion over electrode area. Selectivity of the catalytic systems largely depends on the active adsorptive CO2 phenomena and the affinity of the catalytic centers to the adsorptive carbon monoxide intermediates, leading to their protonation or hydrogenation. In this respect, the presence of such metal oxide additives as tungsten oxide or high surface area hydroxyl group rich zirconium leads to activation and electrocatalytic enhancement effect. And here we also can see that two-layer system, for a two-layer system, we will observe the reduction process at more positive potential. We get higher net current density, and thanks to subsymmetric H-sorption by tungsten oxide structure, we have low evolution of hydrogen. To conclude, two-component hybrid system of iron oxide zirconium shows very high selectivity towards CO2 reduction. Addition of zirconia increases the efficiency of the process. At the iron oxide zirconium hybrid system, the reduction of CO2 begins at more negative potential, and consequently significant enhancement of the CO2 reduction current densities relative to the competitive hydrogen evolution is observed. And in my future work, I will try to further my selectivity and make highly active mixed tungsten oxide zirconium plastic for catalytic iron sites. And thank you for your attention.
Thank you, Paulina, for the presentation. And I would like to thank the speakers of all this part of this morning. That was very dense of science, but also of pleasant memories. So thank you all, and a virtual applause to all the speakers. Now I let the stage to Francesco for the second part of the morning.
Okay, so I want to thank all the speakers too, and I want also to thank Katia for keeping the right time, and excuse us if you have some technical glitches, so we have started a few minutes late. Now let's go on with the next session. It's a pleasure for me to introduce close collaborators and also a lot of students that have passed through our lab, and maybe with a little bit of sadness because let's say they went abroad and they couldn't keep their researches in our group, but I'm very happy for them and for their career. So next speaker is Rinaldo Raccichini from Springer Nature Berlin, and if I'm not wrong, it was the last undergraduate student of Roberto. So please, Rinaldo.
Okay, thank you, Francesco, for the nice introduction. Let me just share the screen. Okay, good. Okay, can you see it? Can you see it?
Yeah, it's fine. You can go.
Okay, so right now, so I would talk about something different, not about technical science as done before in all the excellent presentation that have been shown, but it's something more focused on career development and the role that Roberto Marassi has, especially on me. So just a brief introduction to myself. Right now, I'm working as a senior editor of Nature Communication, and as a scientist, I always had a passion for energy and electrochemistry in particular, and especially for scientific communication. The reason why I have electrochemistry, I think, is well said by Professor Alan Budd. I think that almost all of you know him when he's saying that electrochemistry, I mean, when you are combining chemical energy and electricity, you are moving a barrier in chemistry, and you can do a lot of different things. For example, you can obtain by electrolysis metallic sodium, lithium, fluorine, chlorine, and I think that it's something that always fascinating me. Indeed, I always have a passion for electrochemistry because I think it's really interesting combining these two types of energy. And this was something lucky for me because in 2010, I was lucky enough to meet Professor Roberto Marassi when I was master student at the University of Camerino. I went to his advanced analytical chemistry module, and I think that his way of teaching was absolutely engaging. And it took my attention, and I wanted to know more what he was doing in terms of research. And he made me aware that he was doing also an optional module of electrochemistry, and I attended all his lectures, and I immediately recognized that what he was doing is exactly what I was looking for. So that's the reason why only after passing the examination, I just asked him to join his research group, and for the end of my master. And during years, I learned a lot of different things from him. Something that's so fundamental for me still right now. So first of all, I learned from him the battery science, all the basics, and also introduced me to understanding what is a scientific publication. And this was essential to me because I discovered a complete new word that I really enjoyed a lot. I learned being an inquiring mind, so thinking about outside of the box and see the big picture of science, not only related to your own field of expertise. The perspective storage in his lab, and encouraged me to extend the skill within the research group. And this was invaluable time because I learned a lot from all the members of the research group of Professor Marassi. And from him that I really enjoyed a lot because he showed how a group leader and a mentor should behave. It was nice to give credits. He inspires a lot of enthusiasm. He was able to help people a lot, and there was a lot of respect. And something that I remember clearly back in the days, in terms of fun fact, we from time to time had group meetings, and they share with us as a group member his life working with during his years research in US. And I think I learned from him two absolutely excellent messages. First is that you have to work hard to pursue your scientific vision and never give up. And second, if you have an idea, you have to develop it, even if your boss do not agree with that. And they tell us a lot of different things happening in the lab when I was researcher back there in the US, and a lot of nice stuff during the group meeting. And this is a picture of the research group that were back in the days, and you can see here some of the speakers that we present today and also presented yesterday. And so after my master, so I wasn't something. You are not the youngest person doing master science, but you have good skills. In a position of Professor Stefano Passerini in Germany, and then that's the reason why I moved from Italy to Germany. And during those years, I mean, thanks to my PhD boss, I was able to going in deep on specific focus of electrochemical energy storage by working into the lab and writing scientific research article and review paper. I also learned about the publish or perish philosophy which ruled the modern academia, so I applied what I learned from Marassi in terms of lab skills. I've further developed additional method of analysis of the research, which allowed me to carry out additional activities as reviewer and an editor for scientific journal. It was also something essential, and this was I was able to do this because of my PhD boss allowed me to dedicate some time on that. So I continued applying the inquiring mind method that I learned from Professor Marassi. And something that I really enjoyed was when he came to Ulm in 2014, and we start continuous discussing back in the days and batteries about what is real role of anodes, or what can you get from a specific type of material. And this is something crucial because even when I was a PhD student, he was able to simulate and train my critical thinking regarding to the state of the art of lithium-ion batteries. And so this was the apply for me in terms of perseverance. And this is pictures of the part of the research group in Ulm when Professor Marassi was visiting us. There is him in here. So at the end of the PhD, I decided that I want to know more about electrochemical methods. So I moved to UK as a postdoc in the research group of John Owen and Nuria Garcia Reyes. And John Owen was, during the year, was my second mentor, was not too different from Marassi in terms of approach to science. And there I learned a lot of a lot about impedance-based method for electrochemical investigation and knowledge on battery system. And I was able also to became a research project reviewer and start to mentor and train these students. And something that I also enjoyed in this period was the help that Marassi gave me, because we're discussing quite a lot about the molten salt electrolyte that he developed in the 60s, because was something not too different of what I was doing as a postdoc in Southampton. So I applied all the skills I learned from him, and because he was also essential in this case to obtain proper experimental results in the lab. When we published a paper on the aluminum sulfur, I was happy to dedicate to him my contribution about this research activity that we had. Another fun fact that I enjoy about Marassi is when we talk about the chapter he wrote in the early 80s on the topic of molten salts for sulfur-based battery, he gave me a really nice opinion on what the difference between probably what's going on today in the academia and how the academia was before. And as you can see, he said, I would never be able to write what I wrote 40 years ago, probably because back then they had typewriters rather than computer, and they had more time for thinking, while right now everything moved too fast. And I know that everyone that knows Marassi can recognize himself in this. After this experience, I decided to move out of academia, because I think that was not my specific career, because I want to fully focus on different scientific aspects of research in the lab, but also outside of the lab. Right. Peter Higgs said in an interview, if we would not be prepared, but single somehow there is an issue to create to pursue something different. I moved to another lab in the UK, in London, when I started doing different research activities, trying to bridging academia and industry, still in in terms of lab skills, mentorship, less experienced people, having an inquiring mind, persevere in obtaining the results. But at the same time, I was enjoying this, but I felt that it was not exactly what I wanted, because I realized that I was moving to senior role, and when you're moving to senior role, you have to spend more time in management and less time into the lab. And especially, I didn't have the proper time to read papers and learn science outside my field of expertise. And so this is something that I consider as a drawback of this type of research position. So I thought that it was a time for change. And I consider what are the options. So I recognize that because especially if you like reading papers, enjoy writing, you should consider a career as in-house scientific editors. And I applied to Springer Nature because Nature Communication was looking for someone with my background and expertise. And some people are asking, so if you are, as an editor, still a scientist, I would say yes, because every day in doing the editorial job, I apply exactly what Professor Marassi teach me in terms of research skills, critical thinking, and data analysis. And so there are several key skills for an editor in terms of be able to evaluate a paper, be timely management, well organized, be able to communicate, and have a big picture. And in general, role of editor have a lot of different things. Most of them, especially for an housing editor, are really interesting because you can also commission different type of articles, review, commentary, front half. You can organize conference, write your own comments, and try to promote the good scientific research, and making a lot of different things that I'm really enjoying a lot. So as a take-home message, especially to people that are still not sure about their career, I would just suggest to choose carefully your mentor, especially during university year, because will be essential for your career pathway. And I also suggest to ask your mentor to ask you in the lab. And if the person is able to help you in the lab, this means that your mentor is a good one. This is, for example, something that Professor Marassi or Professor Owen always, they were always nice to help into the lab. And you should have your vision about science and always discuss with other research and scientists. And in this way, you can create your own network to support and be supported. Never give up when you are in the lab, especially because 90% of the case, the experiments are not immediately successful. And be always curious, expand your knowledge. And also remember that at the end of your PhD, or when you are, I don't know, at the end of your contract as postdoc, there is life outside of academia. And ask yourself what you like most and see if there is something available in the market. So, and thank you for your attention.
So thanks, Rinaldo, for your very interesting and original presentation. Yep. I don't know if there are some questions. You can use the question and answer chat. If there are not, okay, I will skip to the next presenter, which is Marilena Mancini. And okay, so with the presentation, graphite anodes for lithium-ion batteries, from particle design to cell performance. So thanks, Rinaldo, and please, Marilena.
Yep.
Thank you very much. Can you see the presentation?
We see...
No.
No, we see the screen. Now we see your face. Are you able to share? Yes, you are able to share, I guess. You should share the screen and then open the presentation. This is the easiest way to do it. At least the way they should work.
Now.
Okay, now we see it. Thanks.
Thank you very much, Francesco. And thank you also to Rinaldo for giving this nice overview, which I fully agree on the things he has said about the skills of Professor Marassi and what we have learned from him. It is a big pleasure for me to be here today, to meet all of you again, and to give my contribution to this nice symposium dedicated to Roberto Marassi. For this talk, I have chosen a topic, which is graphite for lithium-ion batteries. Because graphite it is used as a preferential anode active material since the introduction of lithium-ion batteries in the market. And still today, it has 90% of market share. And even with the introduction of other materials in the anode development, like silicon, there is a strong demand increase expected during the next years. Nevertheless, natural graphite has been recognized as a critical raw material by the European Commission, as has been already mentioned yesterday. And this is because most of the production and processing of graphite is nowadays made in China. There is a lot of work and efforts going on to increase the product quality, to decrease the cost and the impact on the ecological point of view of the production of graphite. And we know very well that fast charging and low temperature applications of lithium-ion batteries are still currently limited by the graphite. It is very important to work when we want to design a material for lithium-ion batteries from the material design to get cell performance. And this is particularly true for graphite, as most of the physical characteristics of the graphite particles reflect the electrochemical performance, especially for those parameters which are critical for the performance, but also the safety of the lithium-ion battery. There is a strong correlation between electrode properties, material properties, especially when we speak about graphite, but this is also true for many other active materials for lithium-ion batteries. And these electrode and material properties, they both contribute to the overall cell properties. When we speak about fast charging, it is a very hot topic today, so due to the challenges to recharge our future cars, electric cars, within a few minutes. And what we know is that the intrinsic kinetic limitations will lead to some problems, not only in terms of performance, but also in terms of safety. And the reactions rate at the electrolyte interface, it is one of the dominant factors. Therefore, when we want to design fast charging and the temperature applications of lithium-ion batteries, we have to work at different levels of the optimization. From the active material itself, but also electrolyte, cell design, separator, cathode, interfaces, procedure for charging the battery and balancing. But mainly what happened at the interface between the anode and the electrolyte, it is the most critical to determine the kinetic of the overall mechanism. Because in this part of the battery, the charge transfer of lithium occurs by crossing different steps, which are all important to effectively work in the system. Well, the kinetic at the anode interface has been largely studied at the University of Camerino during the years where I started joining the group. This topic of graphite was already started by Sonia a few years before I joined the group. And I started working with Professor Roberto Marassi in 2006, where I've got my position as a PhD student there. I was completely new regarding electrochemistry and lithium-ion batteries, but within few years of work, supported by Francesco, Sonia, and all the group of Roberto Marassi, we could work quite a lot on this topic. And 1 year after, in beginning of 2007, Marassi has organized for me a 6 months period at the Center for Solar Energy and Hydrogen Research in Ulm at the research group of Margaret Wolfart-Merens, where I joined the first time. And this was only the beginning of a long-lasting collaboration. And here I put some pictures of the group of Roberto as it was in that years, with collaborations with the different PhD students coming from different universities, both in the field of lithium-ion batteries and fuel cells. And this was the group of Margaret Wolfart-Merens in 2007. Nowadays, the group is quite larger than that. And the collaboration started, and it is still very open and active. Beside this collaboration, Roberto Marassi was very open to collaborating with other realities, both in academia. Especially, we had collaborations with University of Chieti, Bologna, Roma, and some of those results of this collaboration were already discussed yesterday very nicely from the speakers. And in 2009, we also started another topic in Camerino, which is related to the use of water-soluble binders for producing the anodes. And we have applied successfully this approach not only to graphite, which is nowadays the state-of-art processing for graphite, the use of aqueous binders, but also to other systems like silicon carbon materials and titanium dioxide anodes. So here, briefly, it is an overview of the main results, which were then part of my PhD thesis. 15 years ago. Sounds very a long time ago. And the main work was done by optimizing the kinetic at the interface between the graphite anode and liquid electrolyte by using some tin metal layers, especially copper and tin, were employed, which gave faster charge transfer reaction, which then translated to increased low temperature capacity, and in the case of anatase titanium dioxide, very high rate performance. Another approach was to use nanometals dispersed into the electrode bulk, and this was also part of the thesis of Mario Marinaro. And there was already an attention to tailor the active material properties. In the case of graphite, we perform mild oxidation, and in the case of titanium dioxide, thanks to the collaboration with the University of Ulm, the tailoring of the pores to a mesopore range. What's going on today? So as I said before, charging in a short time, it is a key request for lithium-ion batteries application in automotive industry. And it is still very important to investigate and optimize the kinetic of the anode. Recently, in the past 3 years, I have joined a national project in ZSW, where we take care of shaping of graphite and understanding how the shaping affects the kinetic of the anode. From a geometrical point of view, here you can see that there are different expected tortuosity of the electrodes depending on the orientation and on the morphology of the particle of graphite. What we have investigated in a project called Rondo, how the particle morphology affects the anode kinetic. From a geometrical point of view, it is clear that spherical particles lead to lower tortuosity than particles which are more flat. So the so-called spheroidization process, it is a key process step during the production of commercial natural graphite, and it is very important from industrial point of view. In this process, the flake graphite, original flake graphite, it is converted from a raw material into a very sophisticated high-tech product where there is a strong control of many parameters of the final particles. What we have done during the past few years in ZSW is to use a lab scale process for spheroidizing the raw material and then tailor the final particle size distribution to a very narrow range to be able to use this material into lithium-ion battery anodes. Unfortunately, there is no time to go too much in detail, but what we have investigated very carefully is the effect of the changing of the milling parameters, not only on the morphology, but also on the particle surface. And we have analyzed the particles from a large number of samples produced by several analytical techniques, including Raman, nitrogen physisorption, and oxygen chemisorption. So here I want to give you a short overview of some of the results obtained in this project. And here there is a scheme where I show you different process parameters and related products. And we have selected for this study specifically two materials produced with different conditions. As you see from the morphology, both of the materials have a potato-shaped morphology, so the spheroidization was successful. But nevertheless, there is a difference between these materials, and in the whole range of investigative parameters, we could analyze all the different parameters. The aim was to find the relationship between spheroidization parameters, particle properties, and electrochemical behavior. In particular, we have applied, beside the classical techniques and the standard analysis of density and particle size distribution and surface area by BT analysis, we have also applied oxygen chemisorption to analyze how reactive is the surface of the graphite particle after the treatment. And here you see that there is a big difference between the two samples of natural graphite in terms of release of oxygen-rich gases, which means that by changing the parameters of spheroidization, you get completely different surface chemistry. And another method we have applied to analyze more in detail the complex nature of the surface of the carbon is to analyze the surface heterogeneity in terms of share of defect, basal, and prismatic planes by using the results from nitrogen physisorption and applying DFT model calculations. What we can see from electrochemical point of view is that indeed the material which shows more defects on the surface and more oxygen-rich chemistry correspond to material which offer a lower impedance response in hard cells measurements. And by calculating the different parameters out of the impedance analysis, we could see that the charge transfer resistance, it is quite lower for one sample compared to the other one in a quite large range of temperature. We have investigated these parameters between 20 and -10 degrees C. And you see the charge transfer drastically reduces for the sample Ng2. What this means in terms of performance, in hard cells measurements, when we use very thin electrodes and not applying any pressure, we are able to directly correlate the electrochemical response to material properties and get rid of all these parameters related to the geometry and parameters at the electrode level. And in this case, we see that natural graphite particles with surface defects and oxygen-rich group, and especially high share of prismatic surface, offer faster kinetic at the interface, electrode-electrolyte, and lower polarization, which then correspond to higher capacity under kinetically limited working conditions, in this case, low temperature and also high charging rates. What we think is that we can monitor, we can tailor with a better understanding of the process parameter, which depends really much on the machine and the method used. We can tailor the surface properties to offer sites for faster lithium intercalation. And I took this picture from literature, and it is a nice example of what I mean. So when we don't have nice surfaces open to intercalation, the lithium has accumulate on the surface and eventually leads to lithium dendrite and lithium deposition. But when properly tailoring the surface properties, then we can faster intercalate the lithium. There are different examples in literature, but they all request some treatment like oxidation or exfoliation or other treatments, which the same result can be obtained by monitoring the spheroidization. As I said before, at the electrode level, when we speak about practical application, we have to go to electrodes which have higher loadings and densities. And also in this case, while taking into account the effect of the parameters at electrode level, we can still observe a difference between these two materials. So that means even though the morphology looks very similar, the different materials offer completely different performance at the electrode level. It is very important also to check the processability of the materials. So we have extended the processing of the materials from lab scale to pilot line scale to have larger electrodes and be able to test the electrodes in full cells versus NMC. And here you can see the results or a short overview of the results, and graphites produced with tailored parameters during the spheroidization can be directly used in the cell by offering good cycling stability, and by tailoring also the charging procedure, it was possible to reach 80% of state of charge within 15 minutes, which was the final goal of the project. Then, yeah, I'm finished with the presentation, and I would like to thank very much the people which have contributed to this work, in particular Dr. Irene Ruggeri, which joined our group since 2 years, and she came from University of Bologna, and the PhD student which is currently writing his thesis on this topic, Jan Martin, my boss, Dr. Wolfgang Merens, the project partners, all of you for organizing this very nice and important meeting. And finally, let me thank again Roberto. Roberto has been not only a key figure in the electrochemistry of energetic system in Italy, but it has been also a brilliant scientist with a strong personality and also an inspiring example of devotion to the job of doing science. I want to share with you those pictures taken during some barbecue party at the Department of Chemistry. And this was in 2010, 2011. This is a picture from my wedding, already showed by Margaret before. And this is a picture of the group in the time when I joined the group of research of Roberto. Roberto has followed my progresses during the whole time, even after I left Camerino. So thank you very much again. Thank you for your attention.
So thanks, Marilena. This has been very interesting. You have been very kind to share pictures at the barbecue parties in which we were all in good shape. And okay, I think there is time for one question, if there is.
I have one question. Is Rinaldo here?
Thanks.
Thanks for the nice presentation. I really enjoy the fact that you're tailoring the graphite particles. But I've seen that all the research works, I mean, in order to obtain fast charging using graphite anodes, are working on the electrode processing part rather than particles. For example, trying to implementing in a abstractive way the porosity and tortuosity of the electrodes. Is it something that have you measured, or do you have planned to do something concerning this topic?
Yes, in this project, we have analyzed how the density, for example, of the anode influences the fast charging performance by keeping constant the graphite. And we have keeping constant other parameters while changing, for example, the graphite produced with different methods. And yes, you're right. There are, as I said before, there are different levels where efforts are made, not only on the electrode level, but also on the active material itself. And both approaches were to be investigated and put together to get finally safety together with fast charging results.
Okay, thank you.
So we have also analyzed some defect of this of the porosity of the electrode, the tortuosity of the electrodes, try to correlate it with avoiding lithium plating. But the results I could not show all in this short presentation.
Okay, thanks.
Okay.
Thank you, Rinaldo.
Thanks, Marilena, again. And now it's time of Maria Assunta Navarra from Sapienza University of Rome with the presentation Electrode and Electrolyte Materials for Fuel Cells and Lithium Batteries.
Okay, thanks Francesco for the introduction. Let me share the screen. Yes.
Okay.
Let me know if everything is working.
Yes, it is.
Okay, fine. Okay, so good morning, everybody. It's a great pleasure for me today presenting some activities developed at the chemistry department of Sapienza on fuel cells and lithium batteries. These indeed are two important topics shared with Roberto Marassi that gave me the opportunity to interact with him. I met Roberto Marassi the first time in Rome in 1999 when I was a master student in Bruno Scrosati's lab, and since that I can remember many round-trip journeys from Rome to Camerino, in most cases by Bruno's car. And actually they were not only scientific meetings. I could experience a real friendship and a mutual respect between Bruno and Roberto. And this is something that I will never forget. Over than 30 years, many projects were developed at Sapienza in collaboration with Roberto Marassi, by Bruno Scrosati, and also by Stefania Panero. And among all, I want to mention the NUME project funded by the Italian Ministry of Research. That was a huge cooperation on a national level on fuel cells. And actually it was my first, most important chance to interact with Roberto Marassi. Also another very important project for me in collaboration with Roberto Marassi and many other partners also present today at this symposium was the European project EPOLS on a polymer electrolyte lithium batteries. So today I'm leading the ENAM group of the chemistry department of Sapienza, trying to keep ongoing activities on both the batteries and fuel cells. And I'm proud to follow in footsteps of my mentors, maintaining the collaboration with the University of Camerino and in particular with Francesco Nobili, my friend and colleague. So let me now go into the scientific part. As already mentioned, I'm dealing with conversion and storage systems that I like grouping under the definition of hydrogen-related and lithium-related topics. And today I'm going to briefly present some results on fuel cells and lithium batteries. In particular, I'm interested in the polymer electrolyte membrane type fuel cell, that where the energy, the chemical energy of the hydrogen combustion reaction is directly converted into electricity. Unfortunately, some limitations still exist on this technology that are related to the polymer electrolyte membrane asked to work at higher temperature and lower relative humidity, but also to the catalysts that are used as electrode components and still based on high-cost noble metals. So in order to improve the properties of the polymer electrolyte membrane, a strategy consists of the incorporation of acidic metal oxide in a Nephron membrane. That is the most famous polymer electrolyte used in fuel cell devices. Starting from our first study on sulfated zirconia during the NUME project in 2007, we actually investigated many compounds of this sulfated metal oxide family, all of them having very high acidity, able to enhance proton conductivity in Nephron. And one of the most recent, actually even the most interesting compound, was sulfated titania. We synthesized this compound through a convenient one-step sol-gel synthesis, resulting in anatase particles with a very homogeneous round-shaped morphology, a good surface area, and a very high ion exchange capacity, even higher than Nephron itself. These particles were used to realize nanocomposite Nephron membranes. Of course, in order to investigate the effect of the filler, several compositions were studied, and these membranes were used as electrolyte in a hydrogen-air fuel cell devices by adopting commercial benchmark platinum-based electrodes. Here I'm showing the results of the fuel cell test in terms of polarization and power density curves recorded under very critical low relative humidity of 30% and cell temperature increasing from 70 to 110 degrees. If compared to a plain Nephron membrane, here showed in black, our composite membrane containing 5% of sulfated titanium Nephron really had better performance, especially when the temperature reaches the target critical higher value of 110 degrees. In this case, indeed, the composite membrane allowed higher current and power densities, probably thanks to its hygroscopicity and acidity properties. Besides the polymer membranes, we are also interested in the catalyst materials for fuel cells. And we were wondering if our metal oxide particles could have a catalytic effect to be used as electrode component in order to reduce the total platinum loading. As you know, such catalytic properties can be conveniently investigated by an electrochemical technique that is based on a rotating disk electrode, that is pure electrochemistry. And let me tell you that Professor Marassi was really mastering this technique. He had a huge knowledge, both theoretical and experimental, on this matter. And that's why I spent a short but very intense and also funny period in his laboratory in 2007, enjoying his teaching on this topic. So as a catalytic material for fuel cell, we were recently investigating the perovskite calcium titanate that was demonstrated to be a good co-catalyst when added to platinum. In this, indeed, when it's used together with platinum, the electrochemical surface area of the catalyst really improves. And also the oxygen reduction reaction is enhanced. And these improvements are probably due to oxygen vacancies present in the structures and in the stoichiometry of the perovskite. Let me now jump to the lithium-related topics. The lithium battery technology has been already introduced today and yesterday, so I don't need to introduce it. You already know that this technology is already on a very high level of development. Anyhow, some issues still remain. Among these, safety. The problems related to safety and reliability are mainly related to the electrolyte due to the use of thermally unstable lithium salt and of volatile and flammable organic solvents. A way to reduce the flammability of this conventional liquid electrolyte, such as commercial LP30, is the use of ionic liquid as flame retardants. In this study, for example, we demonstrated that the pyrrolidinium-1,4 TFSI ionic liquid can act as a good flame retardant additive able to control the self-extinguishing time of the electrolyte. But ionic liquids are not only flame retardants. They can be conveniently used for a double positive effect, both at high and lower temperatures. Here, for example, we demonstrated that this pyrrolidinium-1,4 PF6 ionic liquid could enhance the flash point of commercial LP30 electrolyte, thus improving its stability. And also the crystallization of LP30 occurring just below 0 degrees is shifted towards lower temperature and also suppressed with an increasing amount of the ionic liquid. So controlling crystallization, the ionic conductivity decay can be also controlled, and this is another positive effect due to the ionic liquid addition. The mixed electrolyte, composed by 50% of ionic liquid in LP30, was successfully used in a lithium metal cell, in a high voltage lithium metal cell with this lithium nickel manganese oxide Spinel cathode. And here I'm showing the voltage profile in charge discharge, and also let me stress that the Coulombic efficiency of this cell was improved when the current density rate was increased. Better performance were obtained when the mixed electrolyte with 30% ionic liquid was used in combination with a homemade Spinel cathode containing chromium and iron dopant. In this case, indeed, a very long cyclability and good stability was obtained at particularly high current density rates up to 10 C. So ionic liquids actually have a really nice versatility. So their properties can be tailored, and we enjoyed synthesizing new ionic liquids just playing with their structures. In this study, for example, we wanted to investigate the effect of oxygen on the cation ring and on the side chain. And we coupled these new cations with different anions, TFSI or FSI. course, the thermal properties in terms of crystallization of the ionic liquids are strongly affected by both the oxygen modification or the anion structure. For example, an oxygen in the side chain increases the flexibility of the structure, thus suppressing crystallization. On the contrary, a smaller anion structure can enhance the crystallization of the compound. These new ionic liquids were also tested in terms of ionic conductivity, of course, and little higher conductivity values have been obtained with the FSI molecules. This, of course, is due to its higher mobility and lower viscosity, and acceptable values to be used as electrolyte in lithium cells were obtained. Also, when the lithium salt was added, the lithium transference number was considered to be reasonable for practical application. That's why this time we could use this particular ionic liquid as pure main component of the electrolyte together with a suitable lithium salt. And its performance was tested in a lithium cell coupling a lithium iron phosphate cathode. Here the specific capacity and the voltage profile are shown. Then, as I already mentioned at the beginning, an important project, for me at least, developed in collaboration with the University of Camerino was the Apples project. In this case, a polymer lithium battery prototype was developed with a tin carbon anode and a spinel cathode. And the main task of us in Rome, the development of the gel polymer electrolyte, possibly avoiding the use of fluorinated lithium salt. That's why in this project we finally proposed a polymer membrane based on a PVDF polymer matrix swollen by a solution containing a mixture of carbonates and a lithium bisoxalate borate salt. During the project, we also developed a way to prepare in situ during the cell assembly the gel polymer electrolyte, and this particular gel polymer electrolyte composition was successfully tested in lithium metal batteries with both the conventional lithium iron phosphate cathode and high voltage lithium nickel manganese oxide. So with this, I conclude the brief overview of our results in Rome on these two topics, and I want to leave you some positive messages on both the hydrogen and lithium technologies. But before concluding, let me say that it has been a great pleasure and honor for me organizing this symposium in honor of Roberto Marassi together with Francesco and Sonia, that I thank for the many Friday afternoons that we spent together online in the last couple of months. But above all, I want to thank Roberto Marassi for his inspiring teaching and unique example of scientific curiosity and intellectual honesty. This is our group in Rome, and of course I want to thank my mentors Bruno Scrosati and Stefania Panero for their teaching, and all of you for your kind attention.
Thanks, Maria Assunta, for your very interesting presentation. I think maybe there is time for one question, if someone has some curiosity about this project. I remember they were very challenging, but the results were very good. Okay. I see no questions, so maybe we can move to the next speaker. However, I should say the next speakers because we have now a forehand presentation from Arianna Moretti and Agnese Birrozzi, which in some way shared the path, and they will show us. So please, you can go.
Hello. Hello to everyone. I'm going to share with you my screen. I hope you can see something. Please let me know, Francesco.
It's coming.
It's coming, great.
Okay, it's here.
So before starting, I would like to thank you, Francesco, Marassunta and Sonia, for having organized this symposium, for having made it real, a desire of Professor Marassi. I would like to share with you what has been for me Roberto Marassi, that has been not only the prof, so also my mentor, but also has been, as Licia said yesterday, also became over the years a part of a family. I consider him like this. And I think that with many of you share the feeling of missing him very much. Today, I'm going, we prepare a joint presentation together with Agnese, because we both are legally bound to industrial secret. So we could not share with you any data, but we thought about sharing a little bit of our career path, especially can be of interest for the PhD students that are following the symposium. And we made a joint presentation because our career is very similar. We both started to work with Professor Marassi in the field of energy storage and conversion during our master degree at University of Camerino. Agnese, she was busy with the aging test of commercial lithium-ion batteries, while I started working on the catalyst development for fuel cell. And I want to highlight the fact that already at that time, Professor Marassi was very, let's say, promoting the multidisciplinarity of our research topics, and we always had collaboration with physics and geology department, and they taught us already at that time to have the importance of having different point of view on the same scientific problem. And also, since the very beginning, we had industrial collaboration, and this has always been an important point for Marassi, that research can be free and can be basic, but it's also our responsibility to keep always an eye on the need of industry and of society. Afterward, we really liked to work with Professor Marassi and his group, and we both, me and Agnese, decided to also do our PhD there. While Agnese was more focusing on lithium alloying anodes, I was working with lithium iron phosphate cathodes. In our group, there were also, although it was small, but there were many other topics that were going on, so we could also profit from daily and strong exchange with our colleagues. And I'd say a topic moment during our PhD was our period of as visiting students abroad. Agnese went to ZSW in Ulm, working with Professor Wolfgang Merens, and I went in Münster in Meet, working with Professor Passerini. And this has been really a key point in our career. And also, Professor Marassi always highlighted the importance of also having a wide view, so maintaining collaboration with other people, and the importance of a continuous scientific exchange. This is a nice picture that I found that with Professor Marassi and the people in this group, we were not only sharing the interest for science and energy topics, but also for good food and good wine. After the PhD, we move out, we can really say, because Camerino and the lab of Professor Marassi became a little bit like our home. And I went for 1 year. I went back to work in MIT in Münster with Professor Passerini. And in 2014, I joined Professor Passerini at the Helmholtz Institute Ulm, and there also Agnese, she came back to Germany and joined the same group, so we had the chance to work again together in the same research group. There we found a large facility and a wider range of topics that meant that for us, for me and Agnese, meant to have the possibility to work on many different aspects and to really widen our background and improve our knowledge. In the group of Professor Passerini, we also had the chance of doing some project management that became, it was a really great possibility for us because it became really fundamental for our further professional development, and we could also strengthen even more the collaboration with industries. And Professor Marassi also at that time, as already Rinaldo said, came as a visiting professor for a semester. Here is the same picture that Rinaldo showed, and here we have a very happy Professor Marassi. We really enjoyed that semester together there. We were very proud to have him teaching to all the people there electrochemistry, so it has been really a great time. And now I pass the microphone to Agnese that will go on with the second part of our career and presentation. Please, Agnese.
Thank you, Arianna. Thank you. And yes, I will carry on the presentation from this point on because this part I start, our career changed differently. I moved to UK. So I quit my experience as postdoc in the group of Stefano Passerini, and I moved to UK to start a Nexion company, a startup company based close in Abingdon, close to Oxford, with a branch also in Japan. This company, Nexion, develops silicon anode for lithium-ion batteries. This is a startup that now is started a partnership with Baker Chemie, just started recently. Baker Chemie is a lead company in chemical production. For me, it was a very interesting experience because, as you can imagine, a startup is like something between academia and industry. So it was interesting that I had a lot of freedom and there was a lot of creativity in the lab in order to develop new materials. But was good that we were also focused on the industrial target. So we were really facing the most the current challenge of silicon. So why silicon is not really so we were like working on the current problems of silicon to solve them, and so that silicon could be used in lithium-ion batteries. Yes, this was an experience that lasted something like less than 2 years, 4.5 years, and then again, together with Arianna, our path was very similar again. Both of us joined the engineering company. We were back. I was back in Germany. Arianna was already there, and both of us joined some engineering companies, respectively Bertrand and Brunel. Bertrand for Arianna and Brunel for me. So this kind of company are providing services to the automotive industry, in general industry. In our case, was automotive industry, and so. The area of working was still the development of battery system for automotive application, And well, when we start, so for both of us, we had a common experience that when we had our first interview with them, the key point that were coming out from the interview was that, first of all, we should have some technical knowledge in the lithium-ion battery fields. And that was thanks to our previous experience was there. We were asked which were our communication skills. So if we were able to write a scientific report, we were able to present topics in form of PowerPoint and presentation. So they asked us also if we have some experience in project managing. And the last point, very important, that I want to stress these things, was if we were a flexible person. So this is a very important point for this kind of companies because they are dealing with a lot of different topics, also inside the same company. So you should be ready to work in different teams. And I guess that this is something that, yes, that's a key point that very, very important for them. Then thanks to this experience that practically we like allow us to put the first step inside the automotive industry. Now our current situation is that we are both working for an automotive company. So Arianna will start soon in the W group, and at the moment in parental leave, but still working for side events. Of course, the topic, the field where we are working is the development of high voltage battery system. Both of us, as Arianna already mentioned, unfortunately cannot show exactly what we are dealing with, but yes, the different topics, always in the same. And thanks to this experience also in the engineering company, we were able a little bit to see how was a big company, as a big concern like this, how they are working, so what they were looking for. So I have to say that all this experience in a row, starting from Marassi, what you teach us, and our experience project managing in a big group in Stefano, and also they like make a contribution and help us to land at the end on this big company. And the last slide, it's like a picture of us together taken at the wedding of Francesco, actually. And I want to share my personal thoughts, but I think the same of Arianna, she mentioned at the beginning. We want to thank, first of all, the organization to allow us to present this kind of thing. We want to use this occasion to express how grateful and honored we are to have worked together with Roberto Marassi, the professor, not only from the scientific point of view, but from the human point of view, because his human features, like his, let's say, sense of duty, sense of work, is always big curiosity, and be always open to students. Was they are a remarkable feature that yes, we will never forget, and we're always grateful and honored for that. So thanks a lot for the attention. And yes, we miss Roberto very much.
Yeah, thanks, Agnes and Arianna, for your presentation. I don't know, maybe there is time for one question, but okay, so I see no questions, so thanks again. And now we move to the flash presentations that, as we introduced yesterday, are intended to show that the work is still going on. So the next speaker is Antunes Staffolani from University of Camerino with a presentation, an extensive model for solid oxide fuel cells based on impedance time-based deconvolution.
Okay, good morning. Can you hear me? See the presentation? Okay.
Everything is fine.
Okay, very well. Good morning at all, and thanks to the organizing committee for inviting me as a speaker. And today I will talk about a work which has been done in collaboration between the University of Camerino and the University of Perugia about solid oxide fuel cell, and a collaboration which was born thanks to Professor Marassi. And here it is a small introduction before we get started. And SOFCs are quite appealing energy production devices since they don't need any expensive catalysts such as platinum or ruthenium. And they have the highest hydrogen power efficiency among all the fuel cell types. And they can work in a reversible mode, so fuel cell and electrolyzer, which is quite appealing for coupling this system to renewable energy sources. And however, several degradation phenomena can occur during a real operating condition and thus loss of performances, especially when there are temperatures and load variation. So the aim of our work can be divided into two phases. The first one was establish an electrochemical model based on electrochemical impedance spectroscopy, since it is a non-destructive technique and can be applied as an operando technique during the cell running. And the second phase was applying this electrochemical model as a diagnostic tool to detect early stages of degradation. And small experimental details, the cells used in this work are commercial anode supported cells with nickel, yttria stabilized zirconia anode, and yttria stabilized zirconia electrolyte, and gadolinium doped serial, lanthanum, strontium, cobalt ferrite cathode. And regarding impedance analysis, since there were no reference electrode inside the cell, we used the distribution of relaxation time to couple all the processes occurring inside the cell. And regarding the phase one, we applied an extended experimental campaign varying several operating parameters, such as the temperature, the current density, hydrogen percentage, and flow in the anodes, and the airflow in the cathode. And we have seen 5 different time constants, 3 of them related to the anode, which were the hydrogen oxidation reaction, the hydrogen gas diffusion, and oxygen transport, and 2 related to the cathode, the oxygen reduction reaction and the oxygen diffusion. Then we moved to the phase 2. We decided to apply this electrochemical model to detect degradation phenomena in the cell. So we applied a stress test based on high current density, 1.5 amperes over square centimeter. And we acquired the impedance spectra every 4 hours during the stress test. And also we acquired the polarization curve and the reference impedance spectra before and after the stress test. And as you can see from the polarization curve, before and after the stress test, there was a small gap, so the polarization of the cell increased, especially at the high current points. And looking at the potential versus time profile, there was a voltage drop exactly at 16 hours. And at 46 hours, we stopped the experiment since the cell reached the threshold value of 0.6 volt. And in order to add a better view of what was occurring inside the cell, we fit all the DRT peaks with a Gaussian function in order to have information about the area of each peak and the center point, which is the relaxation time. And we plot this information versus the stress time. And we have seen that 2 peaks, PA2 and PA3, related to the anode, the hydrogen oxidation reaction and hydrogen gas diffusion, suddenly change exactly at 16 hours. The area increases and they shift to higher relaxation time. So we did the post-mortem SEM analysis, but the cell was pretty well and there wasn't any irreversible damage, no sign of a delamination between electrolyte electrode interface, nor catalyst particle coarsening. So we did also the micro-Raman analysis, which confirmed that the issues were in the anodes. Indeed, on the stress side, on the stress cell on both side and center, We observed peaks coming from nickel oxide, which is a quite common degradation product, especially when vessels are run at high current density. So concluding, during phase 1, we established a meaningful electrochemical model thanks to distribution of a relaxation time. And we exploited the 5 different time constants, maybe excluding one coming from the inductor in series with a resistor. And by applying this model as a diagnosis tool, we detect a coarsening of a nickel catalyst in the early stage, right before the cell is irreversibly damaged. And in this way, the anode can be reduced back to its prime condition. And I have to acknowledge several people for this work, especially the people coming from the fuel cell laboratory of the University of Perugia under the direction of Professor Linda Barelli. And thank you for your attention.
Mike. Thanks, Antunes, for your presentation. Now the next speaker is Lucia Mazzapioda from Sapienza University of Rome. Perovskite titanate as electrode additive for direct methanol fuel cells. Okay, you can see the presentation, so everything is fine. Open your microphone. Lucia, can you switch on, unmute your microphone?
Okay.
Okay, that's fine. So now we see your desktop. Okay, now we see the presentation. Okay, great.
Okay, thank you for the introduction. Sorry, I'm Lucia Mazzapioda. I'm postdoc in Department of Chemistry at Sapienza University of Rome. Today I'm going to show you a sub-part of my PhD work, which was based on the use of a perovskite titanate as electrode additive for direct methanol fuel cell. The core of direct methanol fuel cell is a proton exchange membrane. The electrodes are in contact phase, in intimate contact with the membrane faces. A scheme of the overall reaction process occurring in this device is here outlined. The advantages of this device are low operating temperature, low emission of coolants, and high energy conversion efficiency. However, there are some drawbacks to overcome, in particular, the methanol crossover through the membrane, the sluggish kinetics of oxygen reduction reaction, and the high cost to allow the direct methanol fuel cell commercialization. A strategy to improve the efficiency of this device was used non-stoichiometric calcium titanate perovskite as co-catalyst for the oxygen reduction reaction, with the aim to improve the stability and the durability of platinum catalyst to support the platinum catalytic activity in order to reduce its loading. The perovskite was synthesized by a soft-gel method using titanium superoxide and calcium chloride as precursor, and pluronic F127 was used as a template and as a reducing agent in order to promote the formation of the oxygen vacancies. The perovskite was characterized by XRD. The XRD pattern corresponds to an orthorhombic calcium titanate phase with an average crystallite size of 145 nanometers. The SEM image shows homogeneous prismatic particles with a specific surface area of about 6.6 meters squared per gram. 4 different catalytic compositions were compared by using RD technique, which setup is here shown. From this preliminary electrochemical characterization, the platinum carbon plus perovskite samples with the platinum perovskite in weighted ratio 1:1 has shown the best performance in terms of oxygen reduction reaction activity. For this reason, it was used at the cathode side of direct methanol fuel cell, whose performance were carried out at 3 different temperatures with 2 molar of methanol concentration. Due to time restriction, just to show you the last condition studied, where we can see how the presence of this perovskite at the cathode side improve the direct methanol fuel cell performance. Especially, it is able to increase the selectivity of a platinum carbon catalyst toward this reaction, showing a lower loss of potential, in particular in the activation and the ohmic regions. Furthermore, at 19 degrees, the maximum power density obtained is one of the highest value reported in the literature under similar operating conditions. Concluding, a non-stoichiometric synthetic perovskite was synthesized by hydrothermal method and used as a additive of platinum for the oxygen reduction reaction. Among all the samples investigated, the catalyst platinum carbon plus perovskite 1:1 has shown the best activity, and it was used at the cathode side of direct methanol fuel cell. And the presence of this perovskite has allowed to work in modulating conditions which are high methanol concentration and a higher temperature with respect to a platinum carbon cathode. I'd like to stress that the adoption of this very low-cost material has improved the platinum stability, but especially was able to enhance the platinum catalytic activity towards the Haur reaction of interest. At the end, this part of this work was done in collaboration with Dr. Vincenzo Baglio and Dr. Annalisa Paolone, and I want to thank my group of research led by Professor Maria Assunta Navarra, and of course I want to thank the organized committee for this kind invitation. And thank you for the attention.
So thanks, Lucia, for your very interesting presentation. Now, last but not least, Anna Chmielniczka, I hope the pronunciation was almost correct, and with the presentation from University of Warsaw, enhancement of copper activity toward electroreduction of carbon dioxide in the presence of tungsten oxide and zinc oxide co-catalysts.
Can you see my presentation?
Yeah, it's perfect.
Okay. So good afternoon. Thank you for the introduction. And today I will be speaking about enhancement of copper activity toward electroreduction of carbon dioxide in the presence of tungsten oxide and zinc oxide co-catalysts. We can see equation of carbon dioxide reduction and potential at which the process is secure. Therefore, selectivity is potential dependent. The biggest problem is the activation of carbon dioxide molecule. It is possible to do this by using metals or metal oxides which absorb carbon dioxide very strongly. Copper and copper compounds are the most promising from the point of view of the catalytic ability, which does not mean it is a practical catalyst. So the important issue during the carbon dioxide reduction at copper-based catalysts are that the hydrocarbons appear the more negative potentials. In addition to carbon monoxide, alcohols formate are expected at less negative potentials. Hydrogen evolution is the competitive reaction to CO2 reduction. The effective reaction mechanism should involve the protonation or hydrogenation of the CO2 molecule, and experiments in acid media could be powerful, but we need more selective catalysts. So we use copper 1 oxide to reduce CO2 in sulfuric acid, because when it is reduced, metallic copper is formed. So to improve the linking of catalytic sites, the initial component copper 1 oxide nanoparticles has been modified with ultra-thin layers of the Killing-time polyoxymetallite phosphotungstic acid. And there is no special differences between using with and without CO2 in experiments, and the net current efficiency is still rather low. So concept of the utilization of copper type system together with metal oxide in acid media includes that the copper catalyst can activate the CO2 molecule, high stability of certain transmission metal oxides in acid media, capability to absorb highly reactive monoatomic hydrogen, and zinc has been identified to be a promising co-catalyst with a wide range of CO selectivity in terms of the Faraday efficiency. So we propose the utilization of copper type system together with metal oxides, particular mixed metal oxide and acid media. So on this slide, we have a CO2 reduction of modified zinc oxide and tungsten oxide nanowires. In graph B, we see typical reducing tungsten oxide peaks, indicating the formation of so-called tungsten bronzes. We have the rather low catalytic activity of tungsten oxides, nanowires, and modified zinc oxides. So we developed a concept of a two-component systems, which are given on the slide, and I will discuss them in the next slides. On the slides, we have a CO2 electroreduction hybrid catalyst of modified zinc oxide with modified copper-1 oxide. Figure B shows selectivity of CO2 reduction with respect to hydrogen evolution. In both graphs, we can see typical reducing copper-1 oxide peaks, and in both cases, reduction is feasible, but net current densities could be higher. On the slide, we have CO2 electroreduction on tungsten oxide nanowires deposited onto copper-1 oxide or modified copper-1 oxide. In figure A, we see selectivity of CO2 reduction with respect to hydrogen evolution. In B, in addition to improved selectivity, electrocatalytic current densities are higher. In both graphs, we have typical tungsten oxide peaks, and we have a high activity of the hybrid system at potential lower than -0.1 volt in acid media. Summarizing, the combination of metallic copper with tungsten oxide leads to synergistic effects during the CO2 reduction. Both components are needed for the effective reduction of CO2 in acid media. Hydrogen bronzing seems to interact with copper size from monatomic hydrogen towards hydrogenation of anionic radical. Tungsten oxide nanowires provide high activity, selectivity, and stability for CO2 reduction. Catalysts based on zinc and copper nanoparticles reduce the evolution of hydrogen during the reduction of CO2. Stabilization and activation of highly dispersed nanostructure metallic copper center with such metals oxides as tungsten oxide and zinc oxide results in the electrocatalytic enhancement of the CO2 reduction, and zinc co-catalyst improves activity and selectivity for electrocatalytic CO2 reduction, mostly to carbon monoxide. And thank you for your attention.
So thanks, Anna, for your nice presentation. Okay, now we are close to the closing remark now. I may ask a question. I will try to make a picture, a group picture. So those that are already connected, if you want, you can switch on your webcam so that we can take a picture together as a real meeting, let's say. Okay. So I'm waiting for someone else to switch it on. This was not my idea. This was an idea of Arianna. I really like it. Thanks. And,
No, this was Katia proposed it.
Ah, was Katia in the beginning? Yes, you're right.
The ownership is there.
It's correct. So let's put
I just reminded because it's an important point.
Okay, I think I see how many of you. Okay, it's enough. Okay, so thanks, Katia, for the nice idea, and Arianna for reminding me. And okay, we take it, and then I will share by email. Okay, so after the picture, it's time for me to for just a few minutes of closing remarks. Even if this is not a closing, this is just a stimulus to keep going, to show that things are still going on. I will start from thanking all the organizing committee. So Marassunta and Sonia, as Marassunta pointed out, we spent some Friday afternoon arranging this meeting. I guess it was quite a success. We have more than 200 connections between yesterday and today. So this demonstrates, I mean, what Roberto made for all of us and for the scientific community. For the organization, I want also to thank the people in our university that helped in arranging this meeting. So Egizia, Monica, and Roberta, and Leonardo and Antunes for the technical support. Again, thanks to all the speakers and the attendees. I think that for all of us, it was a pleasure to meet. Unfortunately, it was possible only in this virtual way, but maybe, who knows, there will be also some chance to meet together all again to talk about science and about the very interesting idea that come out. Because I have to say that this meeting was not just a virtual reunion among friends, but also the level of the presentation was very high. And I think it was very interesting that we talk about science, but we talk also about people. And probably relationships with people was the thing that together with science, Roberto was more interested in. And I also think that the examples that we had of career development can be very inspiring for the undergraduate and PhD students that have taken part into this meeting. Okay, in the end of this, it's very hard for me to add something to all the very nice things that have been said. I think that the figure of Roberto has been remembered in all his aspects. As we were saying, availability for other people, especially the young one, and the enthusiasm for the research, with the mind always looking at the future, open to embrace new research topics. Even after the retirement, his retirement, one of the last experimental activities he was carrying out was on redox flow batteries that at the moment really were on the edge. So I'm smiling because he was involving in it, and really a mind open to all aspects of research. Now we are in a world of research which is becoming more and more specialized, and instead this very broad approach is something that we have to always keep in mind. All of this was supported, however, not only by person, but also by the very hard work, both in studying new topics and making activities in laboratories. The rector always says this, and I have to confirm it that I worked with Roberto for almost 20 years, and the times that I went home from the lab after him, I have to say, were very few. Even when he was involved as a vice rector or in all the official roles, at the end of the day, he always found a time to go into the lab and see what's happening. And even after his retirement, I want to mention, for instance, a chapter of the Encyclopedia of Electrochemistry that we have been working on fundamental principle of battery electrochemistries. And we submitted it in just a few months before his departure. And it has been published in March 2020, and the book has been dedicated to him. So this really demonstrates that he really kept going until the end. And it was moved by curiosity. I can remind one of his teachings. I don't know if I have learned it, but I reminded that was, I can teach you electrochemistry, but I cannot teach you curiosity. Okay, so this is something that you have to put yourself, and it has to move you. And yeah, really a lot of curiosity. He has worked on very innovative fields, from potassium intercalation, study of interfaces, fuel cell, redox flow batteries, immediately jumped on the research on graphene, even before the huge hype that has been on graphene. And also a broad approach, as also Arianna Agnese was talking about. So from the chemometric design of experiments to the data analysis, and also he was one of the first ones, probably, to understand the importance of the multidisciplinary approach to material characterization. One of the first to recognize, for instance, the importance of X-ray analysis, structural characterization to correlate microscopic properties of materials with their functional properties in real devices, and battery, fuel cell, and so on. At synchrotron facilities, but also in lab. I remember that when I started my PhD, that there was still an X-ray machine that was doing X-ray absorption measurement that maybe lasted 2 weeks instead of a few seconds as in synchrotron facilities. But this really was an obstacle. Okay, if we hadn't the real instrumentation, okay, we prepared them. We could them buy. So we could go on this aspect for a lot of time. Just let me remind the last thing that during the 70s, he was a pioneering in the studies for sodium sulfur electrochemistry and sulfur batteries. And last month, together with Vito, we submitted a proposal for a project on sodium sulfur batteries. Okay, so the technology maybe has evolved. Of course, it has evolved, but the good ideas remain and are still valid. So his activity was very relevant, but this counted relatively if it wasn't for the biggest legacy, that he has trained generations of scientists that had success in Italy and abroad. So in this way, the journey that we have traveled through during the last 2 days is still going on and will go on in the future. So thank you, Roberto. Okay, so I guess we are over. Thank you all again. Thank all of you for taking part in this meeting. And okay, it has been a pleasure. I hope we can meet in person to keep discussing on this idea. Okay, bye-bye.
Thank you very much. Bye.
Thanks.
Thanks to everyone. Bye.
Thank you.
Bye-bye.
Thank you.